Hello, everyone. Can we check audio? Do you hear me?
Yeah.
Okay, good. So there's a question on Slido wondering if things have started. They haven't quite yet started. And they don't hear anything, but that might have changed by now. So since the audio is working in the room, I'm going to archive this question. And 1:36 p.m. Is that yesterday? Someone said on time zone. I think if this is my local time, then that was yesterday. And what's the time zone?
So I think we could start our actually first session. Yeah, it will be very interesting today. We have a lot, we prepared a lot of nice talks scheduled for you. And we will start with today with part 2 of Level Up Your Python tutorial by Henry. Yesterday was the first part, so if you would like to catch up later or just to recheck, you could find it on YouTube streaming in HSF channel. Yeah. So Henry, please, are you able to share?
Starting sharing just now.
Great.
Okay. All right, so welcome back. This is the second part of Level Up Your Python. One thing I just want to cover really quickly before we get started with the new material. Last time I talked about debuggers, and I was hoping to do a little demo of the visual debugger, because that's just now, as of about 3 days ago, is possible to do that in the regular IPython kernel. So if I'm going back to that 1.4, so what I can do now is I can define a function with a breakpoint. And then if I click this little bug in the top corner, it opens up a new panel. And this is the visual debugger panel. And I just run that function, and that drops me into the visual debugger. So it hit the breakpoint. It's now on this line. I can actually click and make more breakpoints here as well. I can run one line at a time, and I can watch up here and see the local variables changing. This is a list of all the local variables. This is the stack of all the scopes of it's the call stack. So you'll see the outer level scope, and then function, and then whatever function that's called, and what function is that called, etc. List of your breakpoints, and it'll show you the source, which is obviously just over here in my notebook right now. So there's not nothing very exciting over here. And yeah, eventually you'll step here, you'll hit this error. So it actually has a visual debugger now. You used to have a special kernel for that. Now you can just do it in the regular IPython kernel, as long as you have the most recent versions of everything. Okay, let's jump back and start the material for today. So I promised to move fast yesterday, but we moved a little bit slower. Today we are not going to have that luxury, so we're going to be moving pretty quickly. So let's start. We're going to start with decorators and context managers, then we're going to jump to a couple of packages, and then we're going to talk about using packages at the very end. So let's start with decorators. So a decorator is one of the simplest pieces of syntactic sugar you'll see. It is just a tiny, tiny, tiny little bit of characters saved. So this is what it does. If you define now we're just assuming this line. This is the syntactic sugar. Usually you will define a function, and sometimes it'll be a class, but a function or a class. And then you'll run a line like this. So you'll say, and this is kind of strange because you're getting a function here that takes a function and returns a function. So doing this feels a little bit weird. So instead, you can write it this way. These two expressions are equivalent. When you say at something in front of a function, that will just take the function before it saves the function, it will just pass it through that decorator, that G function. And that's it. It doesn't do anything else. It doesn't even need to return a function. For example, this is a decorator that prints something and then returns 2. Okay, so if I apply it to this function, then it is run because it's basically running this line up here. And the thing it returned is 2. So F is 2. This is a really bad decorator. Nobody expects to stick a decorator on a function and get 2 instead of a function. But that's just shows the point that this is really a tiny piece of just syntactic sugar. It's just a different way to write things, but it really transforms the way you think about these. It makes them incredibly useful, whereas this is an extremely strange construct. This is something that just reads beautifully and is very easy to reason about. So for example, there's actually some built-in decorators. One of them is, one of the most common ones is property. There's also class method and static method. So for example, I'm going to do a static method here. I'm going to use a class called bag of functions. I'm going to stick a static method on it. What a static method does is it allows me to call this function sort of, I'll just stick this one on top, the way we would traditionally call it. So this looks like a normal instance function, but notice I didn't have to pass self in here. In fact, I can call it without calling it on the class, and it's exactly the same. There's a little bit of magic that's happening with the accessor to allow both of these things to work. So I can treat this class as if it's just this bag of functions, because the class, these functions do not require the instance. They do not even require the class. The class method is a little bit more than that. The class is the first argument, and you can do either one, and you can still access what class you're in. Property is another one you'll see used often a lot of places, and that allows you to define a property. So it looks like a member variable, but it's actually a function. That gets right. So this really just, you can treat this like something you would attach to a function that then gives you some feature or something changes in the function. Whereas if you'd use that this syntax, it would have been much more weird passing functions around. And you can also, this thing could be callable. So whenever this is callable, again, it's the exact same, it does the exact same thing. But when it's callable, we call this a decorator factory. And that allows us to add options to the decorator. So another one that you'll find in the standard library is an LRU cache, which is a least recently used cache. And so what that does is it allows you to cache function calls. So for example, I attach this decorator onto this slow function. So I run that. And then say if I do slow 4 seconds, this takes 4 seconds to run. Now if I do it again, it's instant because that's been cached. And you can pass in different options here for the maximum size of this cache that it keeps. And it can also keep track of the types if you ask it to. So using their own example, 3.0 versus 3 will work differently, whereas right now they would be the same. This is statically typed, but I can pass anything I want in here. I'm asking for an int, and I'm saying I'll return an int, but I technically could pass anything I want in here. Only MyPy will care. So a single dispatch is another useful one. If you need overloading in Python, this gives you one argument overloading. So for example, I define a square function here, but this actually doesn't do anything. It's not implemented. And then I use, so this is the decorator. Then this thing I get back from the single dispatch has an extra method added to it. Where it stopped. Okay. So this thing, I don't know if we still need the recording, but it's a thing said it stopped. Okay, good.
Sorry for this. Yeah.
So this thing here is a returns this function that has an extra method, and this method can be used as a decorator. So I can say square.register, and square.register lets me register new overloads. So I give it an int, which returns an int. By default, it will actually read this type information, and will register something with that type. Though you can manually give it a type if you don't want to use the signature. For example, if you're static typing and your live typing are slightly different, usually they're not, but you can give it options. And I can register a string. So now if I call square on a, oops, need to run that. So if I call square on a 2, I get a 4. And if I call square on a string, I get the little square symbol attached to the string. Okay. There's a few other ones that are built into the standard library. FuncTools total ordering is really useful because that will that's actually a class decorator, and that means that all you have to do is define 2 of these things: equals, more than, less than, more than or equals, less than or equals, not equals. We just define 2 of those, and it can't be just the equals and not equals. Then it will compute all of the rest of the ordering methods for you and add them to the class, and you didn't have to touch it. And FuncTools.wraps is occasionally useful. That's actually a decorator that helps you writing decorators. There's actually some excellent libraries that do an even better job. Writing decorators we're not going to get into. It's a little bit trickier to write a good one. So data classes is also a really useful thing. You've already seen this, where you just add a data classes decorator on our class, and then it transforms this class and adds all of the things you would need, like the init and buffer and stuff. You could have done that with composition. I'm sorry, with the inheritance, but the decorator is actually better because you're no longer tied to requiring inheritance from data class. You could inherit from something else if you want, and this just modifies the class. So those can be a powerful replacement. Click is another. There's lots of third-party ones. We're going to see Numba in a little bit. Click is another one that you basically create command line interfaces entirely through decorators. Okay, so let's move forward. You'll be seeing more of these. We're going to jump to context managers. So just very briefly, I've sort of touched on this a time or two before. This is what sort of context manager has a specific purpose. And it is sort of what I call action at a distance. These are actually really easy to use and write. Decorators are super easy to use, but kind of hard to write. So when you open a file, you need to close it. And context managers give you a way to do that. A del statement is just not reliable enough. But a context manager is extremely reliable. So if I say with open as f, this is probably the most famous example of a context manager in Python, then inside this block, f is open. But when I hit the end of the block, the ending action happens, the closing action happens. And once you leave the block, the file is closed. There are actually some really useful context managers in the context lib. So for example, here's contextlib.suppress. So this will suppress any error that you give it. So if you get a 0 division error, anything that happens inside this block can throw that error, and it will just suppress that. It'll exit and it'll suppress that. So this is sort of like having a try and then catching this and then passing if you caught it. But in a more elegant way with one line. So context managers have the ability to run an action later, and they have an ability to act on a error that gets thrown, an exception that gets thrown. So context managers get sort of information for both things. There's actually a really nice tool in the context manager library called context manager. And that gives you a really easy way to define context managers. And it's a decorator, which is why we had to cover decorators first. So for example, I want to set up a timer. This is something I actually write fairly often. So I do a context manager, then I can define a timer. And then inside this, you just use the word yield, which creates a generator, which we haven't had a chance to talk about. But you just use the word yield, and this is where the inside of the context manager happens. And then when you're done, stuff after the yield runs. And in fact, you can even wrap this in a try and finally, if you want to allow exceptions to go through. So you can even get the exception part of the context manager here. So in this case, I start a timer, then I let the block run. And then at the end, even if there's been an exception, regardless of whether there's an exception or not, I will always print the time. So I printed start, I printed end, and you'll see after this was done, I printed how long this took. So this is actually really useful because you can just do a with timer on something. And it even has the extra benefit. Context Manager automatically provides the context decorator. That's what it uses, which is another tool in there. Context decorator allows you to use any context manager that use this as a decorator too. So I can do timer, and there are no arguments here, so there's no arguments here. And I can attach that to a function, and then I can run the function, and now I have, with exactly the same code, I didn't do anything extra. I also get a nice decorator that times functions. If you are coming from another language, I use Ruby a lot, and JavaScript has this too. It has these tools called blocks, procs, and lambdas. Those are the Ruby names. Ruby literally has all three. But that is not what a decorator is. I'm sorry, that's not what a context manager is. You can't do anything here except run the insides. You can't run the inside of the context multiple times. You can't do anything else. All you can do is allow this to run. Right, so this really is only an action at a distance. It's not, a fancier tool than that. This is actually the sort of the foundation for the async support in async.io, and that got added to Python in 3.6. And that's really interesting, but we don't use that in HEP that often, so I don't cover that here. And but it uses sort of all of these tools, decorators and context managers and things, and builds on that. All right, so just to quickly answer the question, you can nest decorators as much as you want. That's assuming they're nice decorators and they return something very similar to what you decorated. Absolutely. Click, did a bunch of them. Obviously, if they return 2, then you can't really apply a decorator to the value 2, but yes, you definitely can nest decorators. Most of the standard library ones are designed to be nestable as well. Okay, so we are going to go ahead and jump over to Numba, which is here. So 3.4 if you're running this locally, which hopefully you are. The links are available. Okay, so let's take a look at Numba now that we've covered decorators. And this is a incredible library. It's really taking, and some of the best libraries in Python take what used to be a language and turn them into a library. Pandas does this. Pandas took basically the languages like R and made them available in Python as a library. So you still get all the benefits of running Python and all the Python libraries, and you can do the sorts of things you would normally have done in some other language. Numba does this with just-in-time compiled languages like Julia. So what you can do with Numba is, yeah, I'm gonna run that. You can take a function that you would define just in normal Python, and you can add this decorator to it. Numba, there's actually several decorators. I'm using numba.vectorize at the moment. Okay. So again, I wrote just a function here that's operating on a, in this case, this actually just operates on a single value A and a single value B. And I didn't add type information, so you wouldn't think that I'm giving type information to vectorize, which I'm not. But this is really just a single value. This is a single value, but it also happens to work on arrays, so it's a valid ufunc as well. Okay, so I'm going to go ahead and just generate some random data, and I'm going to run that first one, and I'm using time it, so it runs 700 times, and it's roughly 2 milliseconds. Now I'm going to run this just once with the Numba decorator. Now this one time, it took longer because it's doing something. It's just in time compiling this and then running it. So the very first time it took a bit longer. But now let's see what happens when I run this many times. This is doing a full time it loop. So this is times, this is timing it one time. This now took 80 microseconds. So this is now has been compiled into LLVM machine code, and it's running basically at the machine level on the raw types. And you get massive speed ups from this for adding a decorator. And often that's about all you have to do. So this is incredibly powerful, and it actually has a bunch of different things. I showed you the vectorize. And this is actually really nice. NumPy has a vectorize as well, but this allows you to write single element calculations. These don't have to be things that happen to work on arrays. They can just work on single values. This is looping over the entire array in machine code and giving an optimized loop over that code. Whereas here I had to make sure everything works in a broadcastable way. And if I added the @numpy.vectorize decorator, that loop happens in Python, so it's slow. And you can also do regular functions here. I'll do a JIT example in just a second. You can ahead of time compile this into a library if you want. You can give it the types beforehand, so you actually pass types to this thing. And then it will do the compile step here instead of the first time I call the function. So if you don't like that first call being slower, you just need to tell it what to compile. You can target parallel architectures. You can target GPUs. I think they're retiring the ROCm, and not enough people are using it. I could be wrong there, but it has CUDA support. You can nest. So the next function, you'll actually see I do 2 just-in-time compiled things inside of each other. And you can create C function callbacks. This is fantastic and lets you write a C function pointer without ever touching C, which is just, it's pretty incredible. And this is useful in several places in Booshistogram and as well as in things. So we're going to do a little example. I usually do other examples. I do a Markov chain Monte Carlo example, which is quite impressive. You'll see that in some of the other materials, so feel free to jump through and look at that. You get, especially for something like a Markov chain Monte Carlo, you get an incredible speed up. So let's just take a look at a ODE. So I'm going to define a function here, this function f, and this is defining an ODE. It's defining a harmonic oscillator here. Okay, and then I'm going to skip this. You can read through this if you're curious, but this is a approximation algorithm here, the Runge CUDA 4, and then I'm going to define this in Python. So I have to loop over steps. So this is a loop but not a huge loop. So this is something that would be kind of nice to be able to compile, but it's not as an easily vectorizable thing. Okay, and then let's just plot that just to prove to you that I'm actually doing something useful. So this is the approximation. I'm actually always kind of impressed at how few points you have to do and how this thing can do very well.
Henry,
If you
in
do,
case, just a reminder, 5 minutes left.
okay. So now I'm going to do this in Numba. So I'm just going to manually call the decorator because I wanted to have both. So this is just the manual expression. Again, I showed you this. That's all the decorator does. So instead of applying a decorator up here, I'm just going to apply them in this line. And then I'm going to run this again. And so by literally doing this, you saw it's the same code. I didn't even bother to go stick a decorator on it. I ran this code here. I've made this over 10 times faster. Okay, and if you want, you can even look at the types there, and they're there. Okay, let's jump to PyBind 11. And this is just a little example of what PyBind 11 looks like. This is, so Numba is really great if you're trying to speed up your own code, but if you're trying to create a fast library, often you want to create something static that you can ship. And so a lot of the libraries in PyHEP are designed this way. And so this is a tool for doing this. And this lets you access C++ libraries. You usually use it to bind, though you can actually just write your code right here, I guess, if you want. And then you write a binding and it looks just like this. So you give it a name and you just pass it the pointer and it infers everything for you and adds it to this module. If you want to compile this, this is sort of what the setup.py would look like. This is what the setup.config would look like. We'll talk about packaging in 2 days. This is an example build system, which grabs PyBind 11 for the build. It's not used at runtime. It's only used to build. And in fact, if you then want to ship this for every known platform, Windows, Mac, and Linux, and all the known versions of Python, this is all you need on GitHub Actions to do that. And that's pretty much almost everything you need in order to ship your little square function that multiplies two things. But there's actually a ton more you can do with this. Here's some examples of different of wrapping a class and things like that. So this supports anything C++ 11 and later. We have specialized support, especially for 14 and 17. Okay. So let's just briefly touch on using packages. We'll sort of cover some of this later as well. So let's spend 3 minutes looking at this. So if you are running a package, if you're installing a package, you'll usually see one of these two things suggested. They're both wrong. This one pretty much never use this. It's better to use this line. This line will install to your user environment if you can't install to wherever you're trying to install to. So it's sort of the equivalent of this, but it's more likely to try to do the right thing. The right thing is to use one of the tools that I'll suggest here, including virtual environments. So if you have an executable, pipx is actually a fantastic tool for running pretty much anything that's an application. Anything that's not tied to a specific sort of set of library stuff that you're working on. So if you do pip install pipx, that's the quickest way to get it, or to use brew install pipx or whatever you're using to grab pipx. And then you can now use pipx instead of pip. It actually it sits next to pip. It's pip and pipx are now sort of worked on by the same people. Pipx, you can say pipx install black. You can now run the black command, but you can't import black. Black and its dependencies do not interfere with anything else that you have already installed. You can even run this in one line. This is great for CIs. GitHub Actions and Azure support this. You can just say pipx run, and then that will download and install and run black all in one line, and it'll keep it temporarily for a week and reuse it. If you've used it in less than a week and more than a week, it'll grab it again. So you have sort of a always fresh, but it's cached for quick reruns. So that's probably the most exciting new tool there. If not, you should be using a tools like virtualenv or venv to set up virtual environments and working in there. Okay, so please read through the rest of this. I think there's some useful suggestions here on how to correctly do it. This is the sort of the replacement for pip install, to set up a virtual environment, activate it. Now you can pip install to your heart's content, and it'll all happen only inside this local folder, which is really, really nice. All right.
Yeah, thank you so much. And I see that you have much more material, so maybe you can advertise people just to go through it by themselves, or some recommendations.
Yeah, I would definitely recommend you look through the rest of the material, also the stuff we didn't cover. I've been expanding that a little bit too. And we will see similar material to some of this on Thursday when I talk about packaging and the PyHEP developer guidelines. So I would highly recommend everyone come back to that that talk on Thursday.
Cool.
And everything else at PyHEP's pretty exciting to do. I would recommend at least that.
Yeah, so about questions, I don't know, maybe I could suggest to move directly to Slack. And like this, we are not behind our schedule, and I believe then it could be even better for some kind of discussions and etc. Thank you, Henry, again. So next one in our schedule is Bruno Alves, and with a super interesting talk about data visualization with Python Bokeh package. So yeah. Bruno, could you share the screen?
Hi.
Hi.
Can you see me?
Yeah, we could see you.
And you should be able to see.
Fantastic. Yeah, not full screen, but
it's easier this way, so I can move.
Okay, great.
Can you
great.
Yeah. Okay, so shall I start?
Yes, please. Yes.
Okay. So hi, everybody. First of all, thanks to the organizers for this nice opportunity. I'll be discussing data visualization with my favorite plotting library in Python, which is called Bokeh, and which I think most of you don't use often. But that is about to change after this presentation, hopefully. So first of all, the motivation. It's pretty straightforward. I would like at the end of this presentation for people to know, to enjoy, and most of all to use this amazing library. And as a disclaimer, I'm not involved in its development in any way. This tool doesn't seem very popular in high energy physics. Actually, in the beginning of the session, people were listing their favorite packages, and matplotlib appeared, but Bokeh didn't. However, it's used in LHCb, and it was also mentioned by the HEP Software Foundation, but it was quickly dismissed, although the arguments they used there are quite outdated now. And as other plotting alternatives, Bokeh is completely shadowed by matplotlib. And this takes me to the second item in the motivation, which is, in my opinion, Bokeh code is, when compared to matplotlib, more readable, is easier to write without always going back to the documentation, which in the case of matplotlib is quite unreliable. And it gives very nice interactive plots completely for free. And then it allows you to build very complex dashboard visualizations with interactions with a bit more effort, but not too much. And that's why it's so powerful. However, matplotlib is still more popular because, first of all, it's older and then more mature, and it has more features than current alternatives. And people have the tendency to resist change. And finally, because when you look for examples in Stack Overflow, you get an histogram, a plot like this, which is comparing how many questions we posted on Stack Overflow using different plotting libraries, and matplotlib completely dominates all the available options. And some of them are quite nice. Bokeh here appears in second, but with a huge difference to the first. And I did this plot already using Bokeh, so you can see already how easy it is to plot stuff and how nice it looks. I'm a bit biased, but you get immediately some interaction for free without actually specifying it. So let's move forward and go for some basic plotting. So first of all, we're going to import some very simple data, dummy data. On here, we're going to import data to perform a line plot. and in the bottom, some data for histogram, which are probably the two most common kinds of plots we do on a day-to-day basis. And how would we do this with matplotlib? Everyone is aware. You have to create a figure object. Then you create an axis and you add a subplot to this axis, which is quite interesting because we are only creating one plot, but still you have to create a subplot. And then if you want to change some property, you have to use setters. And if you're paying attention to the previous talk, you know now that Python has very nice properties that can be used instead. And for instance, if you want to set the title of your plot, instead of applying it to figure, which would make more sense in my opinion, you have to use the PLT, because if you use it instead with figure, you just get an error. So this simply doesn't work, which is a bit counterintuitive. Then when you try to plot stuff, you call a plotting function. What is this plotting? I have no idea. I only know because I named my data set in a meaningful way. This could be plotting anything. It's actually plotting the line. And then you call a scatter plot on top of this to get the markers. Note that actually the plotting line is called before the scatter plot, but it appears on top of the markers, which again doesn't make much sense, and I really don't know why this happens. Okay, then regarding histograms, there are many ways of doing that because matplotlib has two major APIs. So you can do it as in the left, which is very straightforward. I give that. But on the right, you can do again the same kind of thing with subplots, which is really not intuitive. And I think this, the fact that you can do stuff in many different ways gets a bit confusing, especially when you're dealing with figure and axis objects. So to recap, I think matplotlib is a bit hard to use without always going back to the documentation. However, it's more mature and complete. And there are very nice wrappers built on top of it, such as PyHEP or Boost histogram. But unless what you want to do only exists in matplotlib, I would really suggest to use Bokeh. So how would you do Bokeh, the same plots, but in Bokeh? Bokeh, its main idea is to be built around glyphs. And it relies on a layered approach where you start by drawing your figure, and then you apply layers of glyphs on top of it. So first you import what you need. For instance, here we are outputting a notebook, but if you want to output a standalone HTML file, you would call output file instead with a specific name. And then let's try to do the line plot, which is much more intuitive in my opinion. You start by defining a figure, which is empty, so it has nothing in it. Then you define some options, which are assigned directly to the objects you're plotting. And then you plot in order the several layers that you're considering. In this case, the first layer would be a circle. Note that it's not a scatter, although that's also available. Instead, you plot the markers directly, so you know what you're plotting. And then you plot a line. And so when you run this, you get the plot that you're already seeing. Here, if you shift the order of the calls, then this actually makes sense. So the line here appears below the rest. So I think this is very straightforward. If instead you want to do a histogram, here it's a bit different because Bokeh doesn't perform any data processing, almost no data processing at all. And so there are no histogram functions as in matplotlib. Instead, you have to think of a histogram as a group of glyphs, in this case, vertical bars or also quads, which are glyphs with 4 sides. And so you would build an histogram in this way. You would first define again the figure, an empty figure. And then on top, you'd call the quad glyph, which on top will have the value of the counts of the histograms. In the bottom will be 0. And on the left and on the right, we'll have the values corresponding to the edges of the histogram. And then you build the histogram. Just to show you that the figure is really empty, if I comment this line here, you'll get an empty figure and a warning from Bokeh. Simple as that. So Bokeh properties are much easier to set, in my opinion, again. If you want to change something that is related to the figure, you change it to your figure object. And if you want to change some property of the glyphs, you actually refer directly to the glyph, and so on and so forth. It's very customizable. You can do many operations like this one. If you want to search for a specific thing in Bokeh, you can either look into the documentation or do something like this or similar. You can inspect one of many Bokeh models such as axis, but also title, legend, toolbar, and so on and so forth, and then check what's available for you to use. Of course, I've been saying that this is great, but not everything is perfect. In general, I would draw your attention to the last point, which is currently there's no support for inset plots, which are the plots inside plots. This, I think, is the major drawback of Bokeh currently, but it's a current feature request and will be hopefully addressed in the future soon. There are many features of Bokeh that I will not discuss here, but you can check by yourself by clicking on those links. So now let's go to the most exciting part, in my opinion, which is how to do interactive plottings with this library. So again, we start by importing some stuff, the same as we did before, actually. And then I have to introduce you what a column data source is, which is just the basic way in which Bokeh handles data. It's usually required for doing any kinds of interactions, and it's very easy to work with. You just pass to it a simple Python dictionary or a pandas data frame if you prefer using a pandas data frame, but you're not forced to do it. And then things work as follows. So let's try to do the same line plot we did before, but this time using a column data source. So again, we import a column data source on top. We also import a column data source view, which is a way of just selecting a subset of our data. We also import a filter, which will be useful later. And first we define the data, normally distributed in a Python dictionary, and we pass that dictionary to the data source, and that's basically it. We have our data source formed. So now we want to plot the figure. Let's do as we did before. We create the figure object, but this time we specify the tools directly via string, not anymore the default tools as had been used before, and we display the picture. Of course, the picture is empty because we haven't put any glyphs on top of it, although you can see already the tools that we selected specifically before. So let's put some markers on it. Here I chose to put some triangles. And the only difference between this example, which I will show now, and the previous example is that we're passing the source, the column data source, as an argument. And so we can specify the arguments of this call via the names of the variables that were passed to the initial dictionary on top. So X and Y, Bokeh is aware of this because we are passing it a source. Once the source is there, we have lots of flexibility, as I'm going to show next. So let's first create a view of this data set. The view is created here in the bottom. So you have a source. You pass the source to which this view will be applied, and you pass a list of filters. And these filters could be programmed in Python or in JavaScript. Here I'm giving an example for a filter in Python, a Boolean filter, which filters everything that it only outputs what has a value larger than 0. So in this case, we access the data in our column data source, the Y variable, and then we output true if that number is larger than 0. Very simple filter. We again create a figure. We plot some circles on top of it. And by selecting one of many layouts available in Bokeh, you get the plot here in the bottom, which didn't work because I forgot to run something. Just a second. Yes, now it's working. So you can see that on the left, we have the original source. On the right, the view. And since here we shared the range, we immediately get some interesting visualization. You're free to play with this in the browser by yourself. And also, since the underlying data source is the same for both plots, we immediately get some selection tools that once applied to one side are visible on the other side as well. And this was done completely for free. So we didn't have to specify anything in particular to get this. This is very powerful. So in general, there are 3 ways of building some interaction plots in Bokeh. This one you just saw. But if you want to have more flexibility, you can use widgets. And widgets can be used either using a Bokeh server, which has to be running constantly and uses only Python. But I don't think this is very flexible because you need to have a running server for it to work, and it's not good to share. Or use widgets together with JavaScript callbacks, which makes it much more flexible, and the JavaScript required is quite easy. So let's get an example of how to do things with a JavaScript callback. There are many widgets available, some like drop-down menus and so on. Here I'm showing a button, and I'm showing a slider. And these are doing nothing because they are not connected to any JavaScript callback. So now we would like to, for instance, change the size of our markers in an interactive way. So to do that, first we add a variable to our data source. In this case, this called size, which will be the variable that we will interact with from the JavaScript callback, because the interactions are only possible if the variables are stored in the column data source. And then we create our figure. The only difference now is that we are also passing size as an argument. And now the cool part. So we create a callback, which receives two arguments, just args, which are the arguments on the Python side that will be available on the JavaScript side, and code, which is the JavaScript code that you can see here. And then this callback is linked to the widgets using JavaScript onChange method. And once you understand this code, everything becomes clear. So you access the value every time the value of the slider is changed. This will trigger a callback, and you can access the callback in this way here. This is very similar to C. This parameter is the same as the one passed down here. That's why you can access the value. And then the rest is pretty straightforward. You just access the data stored in the source. The source is denoted by S since you passed the S as an argument. And then you loop over the data and you change the size of the marker according to the value of the slider. If you now plot the resulting plot, so you show first the slider and then the figure, you can now control very easily the size of the data points. Not sure you can see that by yeah, now you should be able to see that it's pretty easy to control. You can play with this yourself. You can see how powerful this is because any variable that is stored on a column data source can be changed in any way possible since this is super flexible, right? And the amount of JavaScript code required wasn't too much. So I will now give you a custom example, maybe a bit more useful in general, which is a kind of a, let's say, a dummy exploratory data analysis. So again, we import all the stuff we want. And then we define our data. And here the data is just four kinds of variables, 2 exponentials, 2 Gaussians. You can think of this as, I don't know, the transverse momentum of your variables or the mass of your particles, something like that. And we pass again the data to a column data source here in the bottom. So very straightforward, we get our source. Now we're going to do exactly what we did before, but using a range slider instead of using just a slider. A range slider is a slider with 2 values. And we're defining this time 4 sliders instead of just 1. I could have done this in a loop, but I think it's clear for you to understand that 4 sliders are being created. And each slider will be eventually attached to one of the 4 variables that were defined above. So now they are defined, and we have to link them to a callback. So this is exactly what we did before. We're linking it to the callback. This time, the callback, however, is very simple. We are only adding this line, which I forgot to mention before, is required to make sure the source is updated with the latest modifications you applied. So you look at this and you see that it's really not doing nothing. It's really not doing anything. It's just updating something that didn't get updated. So something else has to be done. And that's what I do in the next cell, where we define a custom filter. This is very similar to the filter I had shown before, the Boolean filter, but this time we are defining the filter using JavaScript as well. The idea is that the filter returns the indices that are only the indices that we want to activate. So we have a kind of a selection. It doesn't matter which kind of selection with the widgets we use. And then we want to return only the indices of the data points we want to activate. So I will demonstrate for it to be clear, a bit more clear. It works as follows. We define a variable called indices, which is just an array with a specific length. We access the start and the end value of our range sliders. We access the data that was passed to this filter as source. And then we just perform a simple loop over all the data source, where the indices will be true if they lie between the 2 values of the slider, and they will be false otherwise. Just that. And then this was defined inside a function so that we don't have to repeat code. I'm defining 4 filters here. And finally, I have to create a view which takes these filters, exactly as we did before. So again, it takes a source and it takes a list of filters. Just that. Now we want to plot stuff to see if this is actually working. So the method you see here is exactly what we did before, but just inside a loop for convenience. We are plotting 4 different figures, one with each one with a different color, and using a different combination of the variables in the original data. You'll be able to see them in a second. And now we can plot the whole layout. And so what did we get here? We got nothing because nothing appeared. Just a second, maybe I forgot to run something. Let me run everything from start. I hope this works now. And it didn't. Let me try again, sorry. So this one works. So I'll have to just refresh the cell probably. Sorry about the technical problems. It should be fine soon. Anyways, there's a version available online in case this for some reason doesn't work. Yeah, okay, no problem. This is not working. I'll show you the example that comes next, which is very similar. It should then let me know if it works on your on Binder. It should actually. It has worked recently. So here, what I'm doing after this is really much of the same. It was just a different way of doing stuff. In this case, I'm adding a variable called color to the data set. Because this time I want to interact with the color. I could interact with anything as long as it belongs to the data source. And I'm defining that color to be gray. And then I'm just creating, again, the figures. And creating a new callback. You can look at this a bit with more detail, but the essential thing is that I'm changing the color of all data points selected to red. Simple as that. Let's see if this one works. So this one should work, I hope. Yes, so it's a bit slow, probably due to the connection, but you can see that all the data sources are the same. These are different views of the same data source. And once you select something on one of them, then the corresponding variables get selected in the others. If you hold the Shift key, you can do multiple selections, which is quite convenient. And so this just shows how much flexibility the whole framework has. And to conclude, there are lots of very cool examples by the community. You can check this. You can also create an interactive curriculum, for instance, online with all these plotting tools. And just to end with a small curiosity, if you really enjoy pandas and you like to do quick plotting with pandas, usually you do something like in this cell, you'd call DF plot method. But if you import the hvplot package, you can actually do the same and have Bokeh working as a backend. If the plot appears. Well, this is a bit slow. It's not working on my side. I hope it works on yours. It was working recently. Anyways, the plot you get should look quite nicer than the plot Matplotlib produced. So I'll end up here. And just before ending, I would like to show you this quick example. Since I mentioned in the beginning that Bokeh produces HTML files very easily, and you don't actually have to do anything. So what I did was just to produce Bokeh, to use Bokeh to extract the HTML file produced directly by Bokeh, and just embedding the visualization directly on a website. This website was created with GitHub Pages, and you can see that it works exactly as in the notebook. And this one is working. So this was extremely easy to generate. In the repository, you'll find a different code with a more advanced example, which I used for a project of mine, and which it was also deployed online. You can see it here, and you can play a bit with it. This just to show that this can actually be very useful for some data exploration or display even directly online using HTML quite easily. So I'll end up here, and I'll take any questions if there are some. And I'm just sorry that this didn't work.
No worries. In fact, I think in case of something, just you will have probably your talk assigned to Python fundamentals in Slack. So I hope you could just continue there your discussion. Meanwhile, I think there is so many questions in Slido. So if you could,
oh, really?
Yeah. So it's good that you wrap up a bit before we could just take more questions.
Okay, let me open Slido. Right. So should I start from the one in the top?
Yeah, we didn't.
Yes. Okay, let's start. So
yeah.
someone asks, should I do it myself or should you select the questions?
No, you go ahead. You go ahead.
Okay, can Bokeh finally export vector graphics like PDF? If you need PDF specifically, I'm not sure. I know that exporting PNGs is very easy. If then you could explain why exactly you need PDFs, because then converting from PNG to PDF, you can use an external tool for that. But the main focus of Bokeh is actually interactivity. So in general, you'd want to have you want to share your plots online. That's why it focuses more on the HTML format. But if your question is only about exporting pictures, now it's very easy to do. Before, I admit, 2 years ago or 3 years ago, it was a bit cumbersome, but now it's very easy. Actually, if you can do it directly from the Jupyter Notebook by clicking on one of the tools. I hope this answered at least partially to the question. So the next one would be, is there LaTeX support in Bokeh? Is there like, so I suppose you mean for symbols? Currently, no. You can use Unicode characters, but as far as I know, LaTeX is still not supported, but you'd have to check. Actually, the documentation of LaTeX is pretty good. So if there's some, the documentation of Bokeh is pretty good. So if there's some possibility, it's there. But I think only Unicode characters are accepted currently. So the next one would be, I think interactivity kills reproducibility. It might be nice to explore the data with mouse, but scripting is superior and kills the argument against matplotlib. It doesn't kill the argument because, as I was showing, even for basic plotting, I think Bokeh doesn't require it to be interactive. So you can just specify no tools, and then Bokeh works as matplotlib. It has the same features. Of course, matplotlib has a bit more possibilities, but that gap is probably going to be closed in the future. So I don't think that kills matplotlib Bokeh at all. And I'm not sure I agree with, I think interactivity kills reproducibility, because as long as you have everything well contained, you should still be able to reproduce what others have coded, right? It looks like plotter wars are the new editor wars. Ease of use is, of course, some of these have to agree to disagree. Of course, this is the whole talk was quite subjective, but I just think if you look at the two samples of code, I just think it's much more intuitive. Okay, but again, there's no way I can prove this. I just showed some examples. I gave my arguments. Probably there are also good arguments for matplotlib. I'm not saying that one should rule over the other, but I'm definitely sure that people should be more aware of alternatives to matplotlib. There's not only Bokeh, but there are also very nice alternatives such as Altair, which builds directly on the grammar of graphics, or Plot9, which is a direct porting of ggplot to Python. In specific, Plot9 has a syntax which is very nice. And people in general don't use these because matplotlib is everywhere. It feels like a lot of boilerplate. Would it make sense to create a style API that uses Bokeh? Yes, exactly. That was what I would suggest. So Ben asked if we should do the same as it has been done for matplotlib for Bokeh. I think definitely. I showed a tiny example at the end. Actually, it would be amazing if there was also support of Boost histogram to Bokeh. That would be super helpful, I think. And also some plotting tool like PyHEP, but PyHEP or something like that. If that's possible, it would be great. You don't have to create. So someone said you don't have to create a subplot or a figure. You're not forced to do that, but you're not forced to do that specifically for very simple examples. When you start to build more complex examples, then it starts to be more useful to use this object-oriented approach, and then you'll find online examples using different approaches, which can be quite confusing. Should I continue, or is this too much?
Let's take a last question, and then we will all move to Slack to channel to discuss leftovers of questions.
Should you then select the remaining questions so that I don't take one randomly. Yeah, for instance, yeah, just go ahead and suggest something.
What I left. What is your opinion on Seaborn and Plotly for data visualization? I think it's the most upvoted. No, there is other one, but yeah.
This is always changing, at least in my browser. So let me update.
I think our helpers, they are removing questions archiving questions that were replied already. Okay. So no worries.
So I'll answer to the one which is not anonymous, maybe, by Matthew Fiker.
Okay, yeah.
Which asks if it has a hardware acceleration backend for intensive graphical simulation, or is it more focused on interactivity? As far as I know, it's focused on both. So you can specify WebGL as an acceleration backend. And if you really have lots of data points, usually this starts to be a problem with around 100,000 data points or so. You can either improve your JavaScript code in the callbacks, because it can make a difference. And if it still doesn't work, you can use higher level libraries such as HoloViews, and specifically data shader. I think it's called this way, data shader, which is specifically done to handle very large data sets by just rendering parts of it. And then each time you interact, you trigger a callback, then it just focuses on a new subset of data. So it's also a nice alternative in case you have really huge data sets. And the examples they have online are very, very nice to look at.
Thank you so much, Bruno. So it was wonderful, and you see so much interest. So you will probably need to go to Slack and reply on all other questions.
That's great.
Yeah. So yeah, thanks a lot. And we are moving now to the next speaker. So it will be Matthew Fiker with discussing about distributed statistical inference with PyHF. Yeah, this year we don't have tutorial about this, but we will probably, it will be more about future plans and other interesting features and etc. So if you would like to know maybe a bit more about PyHF, I think last year was amazing tutorial about it, so you can check. Matthew, can you share the screen? Does it work for you?
Yeah, let me get right on that. Also, can everyone hear me okay?
Yes.
Okay. Yes, I'm going to stop the other screen share. Okay. Okay. Also, Oksana, if I can ask you to please give me a warning at 15 minutes, because I want to try and make sure that I stick to 20 minutes. That would be much appreciated.
Okay, sure.
Okay, thanks. Okay, hi everyone. Thanks very much for coming to this talk. So this is, as was mentioned, this is distributed statistical inference with PyHF, and I'm presenting today on behalf of the PyHF core development team. So that's Jordan Stark, myself, and Lucas Heinrich. And then we also want to call out Ben Galuski for his help in getting a lot of the FunkX stuff up and running. Okay, so today is going to be a little bit different than I originally planned due to some hardware issues. The live demo that I had planned to show today is not going to work due to some issues beyond our control on some servers. So as a result, this all kind of got rewritten at the last moment. And also as another small note, due to what I've now learned is considered a security concern on opening ports, this is not going to be fully runnable on the MyBinder public instance. But as to try and combat that and still make sure that people can follow on if you want, I'm going to try and do all of this live so that if, just to try and show people that if you're interested in following along, that it'll be okay. Okay, so to begin with, we're just going to go to the linked GitHub repository that's on the page. And we're going to go ahead and we're going to get the URL. And then I'm just going to go ahead and clone this down. So you should hopefully see my terminal at the moment. Okay, and then I already have a virtual environment set up, so I'm going to activate that, but if you don't have one, you should hopefully make one as well. And then I didn't really install anything in this virtual environment already, with the exception of just Jupyter and Jupyter Lab, just because those take a little bit of time. But if we go ahead and go into our notebook, then we're now going to go ahead and install all of our actual dependencies. So we're just, and those live under the binder directory. So we're going to do pip install -r binder requirements. And you can see that while we have a few, they all install pretty quickly. They're not actually that heavy. So this should hopefully install for you in just a minute or so. Okay, we're still waiting here for the final bit of the installation. Okay, so now we're up and running, and now we're just going to run Jupyter Lab, and we should get a instance popping up here now. And we're now going to just kind of walk through the kind of toy demo, not really a live demo, that I was originally hoping for. Okay, so this is going to first start off with just a super cursory introduction to PyHF. As Oksana mentioned, we aren't going to be doing a full tutorial for PyHF at PyHEP 2021. However, we have a tutorial that is a Jupyter book that is live all the time, linked here off of the PyHF GitHub organization. And then we also gave a CHEP 2021 talk that's on pretty similar material to this, so we'd invite you to check both of those out. But just in a short sentence, for those of you who aren't familiar with what PyHF is, it's a pure Python implementation of the His Factory family of statistical models. And so for those of you who aren't familiar with His Factory, I'm not going to go into that here, but you can basically just think of it as a family of bin statistical models that has been used quite successfully at the LHC. It's one of the models that was used by Atlas for the Higgs discovery. And PyHF, in addition to being pure Python, also supports optional computational backends such as like JAX or PyTorch or TensorFlow that provide automatic differentiation as well as hardware acceleration on GPUs to try and give you really snappy and speedy fits. And PyHF is also part of PyHEP, and it's designed to have a very clear Pythonic API to try and make it the actual process of model building as simple as possible. And so it's just kind of a very quick example of, here I should probably zoom in to make this more readable. So it's just kind of a very quick example of what doing a simple typical task would be like. We're just going to run the example that's in the PyHF GitHub README. We're just going to import things, and then all we're doing here is we're just creating a very simple one bin model, so that, as much of a toy example as you can get. And then we're going to, once we have this model and some simulated data, we're going to then perform a hypothesis test scan across multiple parameters of interest. We're going to plot those results and then invert them to determine a 95% confidence level upper limit on our parameter of interest value. So we can see that just in a very few lines of code, we can actually get what is known as a Brazil band plot that actually is showing kind of our observed and expected values, as well as the line that would show exclusion. And then we can, as I said, also invert those to actually get the observed limit that we have as well. So this has just been a super cursory overview, but the really important part here is that PyHF allows for statistical modeling of binned models, and it also allows for fast Pythonic fitting. But so the majority of what we're going to be talking about today is going to be focusing on how to extend this with both FuncX as well as Google Cloud platform to try and do high performance fitting as a service. So I'm first going to introduce FuncX, and FuncX is a high performance function as a service platform. So the goal of FuncX is to provide a tool to orchestrate scientific workloads across heterogeneous computing resources. So we're talking clusters on the cloud, on supercomputers, as well as across all different task execution providers. So you can basically write one config that you can model a little or vary a little bit to be able to run on HT Condor, on Slurm, on Torque, on Kubernetes. So it is very extensible and allows you to do be able to switch where you're running with very little change to your actual setup. And it does this by leveraging Parcel, which is a flexible and scalable parallel programming library for Python that is very efficient and quite nice. Okay, so FuncX endpoints are something we also need to talk about here. So they're logical entities that actually are the thing that kind of sit on a compute resource, and they are managed by an agent process that allows FuncX to dispatch user-defined functions to actually run for execution. And so this is kind of the core here. You can define user functions that can then run anywhere on perhaps an HPC environment, and they can be scaled out very efficiently. Okay, so to try and give a very, very short demo of all of this, what we're going to do, since we installed FuncX and the FuncX endpoint, is we're going to do a kind of silly example because I didn't have things working. We're going to try and act like our local machine, in this case, my laptop, is both our execution machine as well as our submission machine. So if I'm acting like I was on perhaps like my HPC center, I can just go ahead and use the FuncX endpoint command line to get some information about what we have here. So the first thing we're going to do is we're going to want to configure an endpoint. And so for this, I'm actually going to open up a launcher again and open up a terminal, because it's going to be actually considerably easier to run this in the terminal than to run it in the notebook right now. So what we're going to do, here, I'll also activate this. Okay, so what we're going to do is we're going to run FuncX endpoint, and then we're going to do configure actually, let me make sure I have this cleaned up so I can try and make it as similar to you as possible. Okay, so if we run FuncX endpoint configure PyHF, then what this is going to do is create all the configuration files necessary to set up an endpoint, and it's going to give us this Globus authorization URL. So FuncX does all of its authentication and authorization through Globus. So the first time that you click on this, if you aren't already logged in, you would be taken to a Globus page for login. And if you're not familiar with Globus, it's a service that does these sorts of things as well as data transfer. And if you don't have a personal account, you can either use an organizational account or your OrcID account or your Google account. So hopefully it's not too much of a barrier to entry that there's this additional layer for security in between. But since I already have this set up, I'm just going to copy this URL, drop that in there. And now simply this is just saying that, hey, you're setting up a new endpoint. Do you want to make sure that you can allow this for authorization for use of the FuncX software development kit? And so we're going to allow that. We're given this authorization key. And since this is a one-time demo, it's perfectly fine that this is visible to all of you. And so we're now going to set that up. And now we get this message that we now have our endpoint configured, and we can go ahead and actually start that up. So before we do that, though, we're going to modify things just a little bit. So as we continue on in our notebook, if we actually look at what this configuration file is right now, we can see that it's basically just a few imports from both FuncX and Parcel. And then we see that we basically have this configuration for the HPC provider, and it basically has these small configuration blocks on determining how the actual workflow is going to run. To make an example of this, we're also going to copy over a configuration file that I prepared beforehand and look at that again. And we're now going to see that in addition to this initialization blocks, min blocks, and max blocks, there's these additional values that I've added in that were default values, nodes per block, and parallelism. Okay, so we're going to explore just what that means a little bit, because without this, funcex might seem a little bit like just magic, and we want to try and avoid that, because you still are responsible for controlling how your compute environment works. Okay, so just to break down some terminology real quick, when we talk about blocks, we're really talking about the basic unit of computing resource that a provider like Slurm could give you. And then the max blocks is then just the maximum number of those that you can have per executor. And the nodes per block is the number of compute nodes that you can request per block. And then this value parallelism, this is basically the value that determines how scaling is going to happen versus just utilizing current resources. So if we take an example from the parcel documentation, which funcex then extends, we can look at this where we have this minimum number of blocks is 1, this max blocks 2, nodes per block 1, and parallelism 0.5. And to try and give an example in a GIF of what that actually looks like, so on the left-hand side, we see this kind of example of having 9 tasks that we want to actually compute and execute. And so what happens is when Parcel and funcex start up, they start distributing tasks to workers available. And so we have this first compute block, and it has the ability to have 4 tasks per node on the block. And so what's happening here is those first 4 tasks are just put on there and start to execute. But then when we get to the 5th block, or the 5th task, we've actually already reached capacity for this initial block. So we now need to determine, are we going to wait for tasks on the first block to finish so that additional tasks can be added, or are we going to scale out to an additional block? And given the way, and given that we've reached a value in the task remaining that is greater than the parallelism of 0.5, what Parcel then decides to do under the hood is it decides to then allocate another block and scale out the additional resources to try and efficiently finish all the tasks. Okay, so with that kind of hopefully in mind explaining a few things, what we're going to do is then run we're going to actually start up the endpoint, and we now see that we have this process running. And if we use the funcex endpoint list function to list all the ones that we have, we now see that we have this this endpoint that's up and running with this endpoint ID. And so this is all kind of on our imaginary remote HPC center or something, but we're going to want to have access to this endpoint ID elsewhere. So we're going to then just put that into an endpoint ID text file, which you would then be able to SCP down to wherever you're running locally. And now if we kind of switch over our mindset to thinking that we're now on our local laptop or we're somewhere else, we're going to now try and set up what we're actually going to run on this endpoint that we've just set up. So here what we're doing is we're going to prepare a very, very simple example as just kind of a test function. And so here we have this simple example function that simply all it does is it basically takes a trivial model, and then it makes some pseudo data from that, and then just performs a single fit. And then, and you can see since we're executing functions, we need to include all of our imports inside the function definition because they're going to be sent off and run outside of a global scope of a particular file. So if we...
Yeah, it's like, I don't know.
5 minutes?
60.
Okay, great.
No, it's not 5. It's just past like, I don't know, 17 minutes of your talk. So you still have a lot of time.
Okay, great. I'll still try and speed along. So thank you very much, Oksana. Okay, so if we then look at this simple example, we see that we then get this just dictionary back, as I mentioned, that returns both the observed fit value as well as the fit time. If we were then to actually spin up the local funcex client that's going to be doing all the communication for us, we can then initialize that, and then we can register the function that we just created with the client. So the client now knows about this function, and it can now interact for us with our remote on our HPC center or something. So if we open up now this this endpoint file so that it's we have this endpoint ID known to us, then what we're going to now do is we're going to serialize this function that we just created, and we're going to have the funcex client send it over the network to this HPC center or to the endpoint wherever it is in the world. And we're going to now ask that endpoint to please execute this task for us. Of course, here, this is just happening locally, so it basically runs instantly with no time. And then in the scenario, we could like wait for a little bit, and then once we think it might be done, ideally you would do this in some sort of periodic checking loop. We can now have our local client call out to the remote center and ask to get back the result, and we see that we get this back. Okay, and so in the interest of time, I'm going to kind of stop here for the funcx portion, but I'll mention that this demo wasn't super interesting because we weren't actually running on a real center, but as was shown in our VCHEP 2021 talk, when we do actually run on an HPC center using funcx and executing code locally from our laptops to then call out to it, we're able to fit 125 signal model hypotheses that are from a published Atlas analysis in a wall time of under 2 minutes and 30 seconds. And that includes includes the downloading of all the files from HEP data to a local machine, serializing them, sending them out, actually doing all the running and getting all the results back. So this can be a very powerful workflow. Okay, so in the time remaining, I'm going to now switch tasks again, and I'm going to actually kill this, and then I'm going to go to a local example of using Google Cloud Platform to try and do a similar thing. Okay, so Google Cloud is a resource that some of you might be familiar with, and I'm just going to run this in the interest of time to make sure that we get going. So Google Cloud is another way for us to try and run PyHF in a distributed manner. So what I'm doing right now is, oops, let me restart and clear all output. Sorry, hold on. Okay, this is strange. The kernel seems frozen. Let me try and restart real quick. Okay, so Google Cloud is a resource that that some of you are probably familiar with, and Google Cloud is another way for us to actually register functions with Google Cloud beforehand, and then to try and run them in a highly distributed manner. And so what we're doing right now is we're actually we're downloading a published Atlas analysis and from HEP data. So here I'm going to copy this URL for a second and go there. So what we're doing right now is we're downloading, that's the actual tarball. We are from HEP data. We are downloading all of the files. Okay, apparently that doesn't want to work, but we're downloading all the file data for this particular analysis. And then we're sending them out in real time to Google Cloud to actually run fits. And then as those results run and come back, we're updating a plot in real time to actually see as these different fit results come in, how they update our final exclusion plot for this supersymmetry analysis. And so as this runs, you can see that as we get more CLS values back, we start to form this exclusion contour. And this is and as we get more and more results back, this will approach the final exclusion limit. And when that's done, it will go gold. Okay, so I think since I'm over 20 minutes now, and this is just going to kind of run and update as things go on, I'm going to stop here and pivot to Slido to try and address any questions or comments that people might have. Okay, and yeah, so now, okay, that got a little bit strange, but so now we have in a runtime of in a runtime of just a very short number of seconds, okay, it doesn't print here, but in just a few seconds, we're actually able to get this this nice plot out so we were able to compute a couple hundred different CLS values and I think under 2 minutes. So this is another example of how we can use distributed computing to take the Pythonic nature of PyHF and run at scale. Okay, all right, so as I said, I'm now going to switch to any questions on Slido. It seems that we have one. Is there any way for users to sync their Python environment with the FuncX service? I assume imported modules need to be installed there. Yes, so that's a very good question. I would have actually shown that had I had access to the hardware today. But when you are setting up your FuncX environment, your FuncX endpoint, you need to recreate the runtime environment that you would need if you're going to be running locally. So that means that, let's say that you are running on some HPC center and the worker nodes would need to be able to set up a particular environment, either be it with a requirements.txt in a virtual environment, or maybe something like a Conda environment. As part of your setup in your FuncX configuration file, you would have the worker call the setup script that you would normally use to activate that virtual environment. So you do need to make sure that on your endpoint, which I've just been referring to generically as an HPC endpoint, that endpoint has the ability to set up the same virtual environment that you would want if you were just running locally. Okay, I think that's the only question we have. We still have, I think, like 3 or 4 minutes. So if there's additional questions, I'm happy to answer them. And if not, then we can go ahead and get going on to other talks.
Matthew, can I ask a question? I somehow cannot type in Slido. Oh, okay, there is the other one. I will be next.
Okay. How does PyHF compare to ZFIT and HEP stats? Maybe they're not correlated, but they seem to be similar. Right. So this, so thank you for being familiar with the scikit HEP ecosystem. I think maybe the thing that's the most comparable is to talk about how ZFIT and PyHF differ. So PyHF focuses on bin statistical models, where ZFIT is trying to do the more general thing of kind of the open world of statistical models in a similar way to what how RuFit does. PyHF focuses on binned models. PyHF though we are backend agnostic. So we have you mentioned, okay, sorry. Yeah, so I think this is kind of this and the question below is a good example, is probably a good example. So PyHF has you can choose, we're backend agnostic, so you can, the default backend that we provide is NumPy with a SciPy optimizer, but we additionally support combinations of optimizers as well as computational backends for JAX, TensorFlow, and PyTorch. And so we have implementations for all of these that the user can switch out very easily. And as this kind of goes into the, okay, so I believe Jonas is going to be talking either today or tomorrow. He's going to do a full tutorial on ZFIT. And is a ZFIT backend a possibility? Possibly, however, ZFIT as of at least PyHEP 2020 is TensorFlow only. And so so this is something to explore a bit more. But I mentioned that this is pure Python, but the commenter mentions that this is often misused, C in the backend. So I guess this is, well, C in the backend is a bit of an interesting comment because, I mean, you know, Python itself is in C, and I guess this kind of also gets into the question of what is a package, because I think most of us would say that SciPy and NumPy, these are Python packages, but as we know that these also have components of Fortran and C in them as well. So I guess I would say, like, when I say pure Python, I mean that that everything that the PyHF development team writes is just Python. We are not actually writing any C extensions or any Fortran extensions or anything like that. And everything that exists in PyHF is installable from PyPI or Conda-Forge if you want. I realize the Conda-Forge brings in the difficulties of the fact that you can install root with Conda-Forge. Great work, Chris and Henry there. But basically, I just mean it's pure Python. We only write Python in the project file, in the project itself, and everything's available in PyPI. The performance of PyHF versus the HIS factory implementation and root, I guess I would say is comparable. And in particular situations, we have been able to demonstrate that PyHF is able to outperform the HIS factory implementation and root due to the fact that we are able to leverage this automatic differentiation as well as the highly vectorized nature of the code. That's not to say that every single instance of every single HIS factory problem that you want to run with PyHF is going to be always faster than the implementation in root, but we've noticed that in many it is. Okay, I think, oh, sorry, and go ahead, Oksana, you had a question as well.
No, I will go through Slido and then maybe Slack. So yeah, so let's move to all questions after to reply in Slack. Well, if you wanted to show something, then we need to wrap up because it's kind of 30 minutes.
Yeah.
Yeah, thanks.
So I'm done at this point. So thanks everyone very much for your attention.
Great. Thank you so much, Matthew. And I hope there will be a lot of fruitful discussions in Slack afterward. So, okay, next one in our schedule is Alex Held with a talk about bin template fits with Cabinetry. So, Alex, please go ahead.
Thanks a lot. Yes. Thanks a lot for the introduction. We're going to be talking about Cabinetry here next. And this is a notebook talk, but we're starting with a few slides just to set a bit the general context. So bin template fits with Cabinetry. There's a few questions that you might ask first. So first, bin template fits, why do we care about them? We use them widely at the LHC and beyond for statistical inference. In fact, we've just seen in the previous talk, PyHF presented, which is something we can use for bin template fits. And in fact, we'll see it again here in this talk. And there's one particular model that also Matthew described called HIS factory that is used for bin template fits. There's a small set of building blocks defined in this model that from which you can construct probability density functions. Even though there's a small set of building blocks, it actually does cover a very wide range of use cases, and it's extensively used in Atlas. Once you have a statistical model defined, you can serialize this to a so-called workspace. Now, the Cabinetry library I'm talking about today, it's a Python library for operating and for constructing HIS factory models. You can pip install it, and we make heavy use of PyHF within Cabinetry. Not only do we make use of PyHF, also of many of the other libraries in the Python ecosystem. And it's written to be modular, so you can use pieces of Cabinetry that you might need, but you don't need to commit to the full thing if you don't want to. Now, working with Cabinetry, there's two main things for which you can use Cabinetry. The first thing is you can use Cabinetry to design and construct a statistical model. You do that from a declarative configuration in which you specify things about your model in terms of physics. So you say, for example, what kind of phase space regions do I want to consider? What kind of samples do I need to consider? What physics processes enter these phase space regions? And lastly, what kind of systematic uncertainties do I want to apply? Then Cabinetry uses this information in that declarative configuration to steer the creation of template histograms. There's many different template histograms you need in practice, and Cabinetry includes the logic to determine which are needed and sends off those instructions to have the template histograms built for you. With those histograms available, then it can build a HIS factory workspace, your serialized fit model. And then with such a fit model at hand, no matter whether you build it with Cabinetry or not, you can go ahead and perform statistical inference. And Cabinetry makes your life easier because it includes diagnostics and visualization tools so that you don't just get back a couple of numbers from a fit, but you can also take a look at them in familiar formats. If you want to design a statistical model, you do that by writing a configuration for this model in a declarative manner. The configuration can be done either in JSON or in YAML, or it can also be a Python dictionary, which we'll see in the notebook section in a bit, and it specifies everything needed to build a workspace. There's an example here in YAML format shown at the bottom, and the idea behind this schema is that you can capture the potentially quite complex interplay between different phase-space regions, different samples, and different systematics in a concise way. There's different blocks here of this configuration. Shown in this example, we'll have a closer look at that in a bit when we talk about this in our example in the notebook that we're going through. So when we have a configuration available, what happens next is we want to create a workspace out of this, our FIT model, and that happens in 3 steps. First, Cabinetry determines which template histograms are needed, sends off the instructions to backends. By default, this is using Uproot. There's also experimental coffee support to obtain the histograms. Then there's an optional post-processing step that can be applied, for example, to have additional smoothing applied. And then finally, everything is assembled into a workspace. In this case, we're using PyHF, and that workspace will be serialized as a JSON file. At this stage, there's already visualization utilities available so that you can ensure you're building the correct workspace. Once you have this model available, Cabinetry can be used to steer statistical inference. And there's many different visualizations that come with that. You see some examples here: parameter correlations, poles of nuisance parameters, upper limits for parameters, ranking parameters by their impact on the parameter that you actually care about. Everything is validated against implementation based on root. So where's Cabinetry going next? It's under active development, and everything I'm showing you here today is available. And in fact, you don't just need to believe that I'm saying this, because we'll see in a second in the notebook, which you can follow along, that all of this is working already. For the next steps, in the short term, an overhaul of the visualization API is planned so that figure handling is a bit more convenient and it's easier to customize figures. Histogram inputs instead of just columnar data as inputs are another topic that comes up quite frequently. You see here these linked GitHub issues if you want to read a bit more. A more sort of technical topic is that we would like to support models beyond just HistFactory in the future. There's an issue here as well. And in the longer term, an important thing that we would like to get working is end-to-end automatic differentiation. I'm not going into any detail in this talk today, but I point you to the NEOS project and see also the related PyHEP 2020 talk if you're curious about this. And you also might have other ideas. And if you do so, please, you're very welcome. Your thoughts and contributions, just get in touch if you have any. So in summary, for this very short intro, we have a Python-based library that allows you to create and operate statistical models. We make use of the Python high-energy physics ecosystem to achieve that. Everything is on GitHub, and you can try it out yourself on Binder. And now we'll do exactly that. I have here a notebook, which you'll find linked to the agenda with a link to Binder. And we'll go through this notebook now to see Cabinetry in action. The top cells here are just installations. If you don't run through Binder, if you run through Binder, you have all the environments set up already. So don't worry about those. If you're running locally, you need a few packages. We start by importing Cabinetry. Cabinetry uses the Python logging module to configure its output. There is a function set logging, which we can use to set some sensible defaults for the logging, but you're welcome to customize this further according to your needs. There's a few other libraries that we're going to need, and we just import everything here at the top all at once so that we have everything available for further down in the notebook. Okay, so what are we doing in this notebook today? We'll create a statistical model. We perform inference with it. Then we actually look at a more realistic model, and we in fact take the model off an atlas analysis and take a look at that one. And there's quite a bit of bonus material for you to look through in your own time. That's at the end of the notebook, which we won't have time to go through today in this talk. All right, let's start by creating a statistical model. As I was already saying in the slides, to create a model, we need to have a configuration that specifies our model. The first thing for a model that is needed is a few general settings. So here's a few general things. We need to give everything a name that PyHF ultimately wants in the workspace that we're going to be building. We need to specify the thing we want to measure. In our case, let's say we want to measure the normalization of some signal process, and we call that parameter signal_norm. We also need to specify where we find our input data. So these here are n tuples, columnar input data. And you see we find that in some folder that's called input. And then there's this sample paths thing here in curly brackets. We'll come back to this in 1 second, why this is in curly brackets. So these are a few general things we need to specify. Then next, it's going to be more about physics. So let's say we need to specify now what our phase-space regions are from which we want to include events. In this example here, the regions is a list, as you can see. We only have a single one. You could add more if you wanted. We call it our signal region. We apply a filter. We say we only care about events with a positive lepton charge. And we use as our observable the jet PT with the bin edges as specified here. This is a toy example. You can play around with this. You can add an extra region if you'd like to see then how this further propagates throughout the notebook. So we have our phase-space regions. Now, what populates those phase-space regions? There's different so-called samples. So one kind of sample that we have is our observed data. In this case here, in this toy example, this is actually a synthetic data set. So it's called pseudo data here. But this is typically what you observe in your detector. Since data is treated specially, we need to give it a flag here so that we say this is data. There's also then different processes, collision processes, for example, that we expect to contribute. Here we have 2 of them. One of them we call our signal, the thing we want to measure. And then there's all our background. Here again, you see the sample paths appearing, and you set that to some value here. So what's happening is we override the setting that was given in the curly brackets. As you see down here, what we set in our general settings, we said everything is in this input folder. And then the sample path setting here is overwritten by whatever we specify here so that we can specify samples in different locations. There's also weights that we can apply at this step per sample, for example, related to Monte Carlo integration. So here we have just 3 different samples. In practice, you may have more samples for more realistic style of analysis, but the method is the exact same. Then systematic uncertainties. In this case, we hand over an empty list. We say, okay, we don't have any systematic uncertainties. We'll add some in a second, but for the simplest example, let's start without any. And then lastly, one more thing we need to do is we need to define a so-called normalization factor. This is the signal underlying norm thing that I told you before. It's the thing we want to measure. This normalization factor acts on the signal. And what that means is it multiplicatively modifies the signal sample with some nominal value of 1. And these are the boundaries over which we allow it to vary. And this is the thing we ultimately want to measure. We want to measure what is the normalization of the signal process in the phase-space region that we have specified. So we have a complete config, and there's a utility here, a validation that compares this config to the JSON schema that Cabinetry expects. This is a good thing to check, because if this fails, then this is a sign that something went wrong. For example, maybe somewhere we had a typo. It doesn't guarantee that everything is working well at runtime. There's additional things that could in principle happen at runtime that we cannot know at this stage just with static validation. Then we're ready with our config. There's an overview here so that we can summarize again what's in our config. We have 3 different samples, 1 phase-space region, 1 normalization factor, and no systematics. Okay, so with this config available now, what do we have to do next? We need to create histograms that give us the distributions of all of our process in the phase-space region that we want to consider. We do this by handing this config to Cabinetry and to this template builder module to create histograms. We say here that the method we want to use is with Uproot. So this opens files with Uproot, creates histograms with Boost histogram, and then saves those to disk. In this case, if you look at the output, you see that we save 3 different histograms, which are the distributions of our 3 samples in the 1 phase-space region. Now there's this post-processing step that I'm also going to run at this stage. It's optional, and here it actually doesn't do much. If you scroll down to the extra material, there's an example with smoothing applied where this post-processing step will do more. So at this stage, we have a few histograms, and it's a good idea to take a look at those so that we verify actually we have defined something sensible. And we do this here with another function that takes again the config as input, because the config includes all the information about all the paths where everything is located now, implicitly defined through the structure that you have in the config itself. We see our histogram here binned in this jetpt observable that we requested with the binning we have requested. Our background sample is shown in blue. The signal process contributes mostly at higher jetpt here in green, and then there's our data shown as well. So far, everything looks pretty reasonable. Nothing seems to have gone extremely wrong. So we have histograms. To make things a bit more interesting now, let's add a few systematic uncertainties before we continue with fits. And to give you an example of some systematic uncertainties you might encounter in practice, let's say we have a 5% luminosity uncertainty. So now we update our list of systematics here, and we actually fill it with something. The first thing here is a systematic we call luminosity uncertainty. It changes the normalization of samples, and it does so by 5% in the up and down variations. This is sort of a feature of his factory with how you specify systematics through his factory. We won't have time to go through this in detail. I'm happy to talk about this more after the talk, but this effectively implements the 5% uncertainty for the luminosity. Another uncertainty here is modeling related. Let's say we have our nominal prediction for the background, and then someone else runs a different Monte Carlo simulator and creates a different prediction, and we want to include that also as an uncertainty. We can do so by specifying that for this systematic uncertainty, look in a different tree that's called background underline varied, look at the events there and build another histogram, and then make a systematic uncertainty out of that. And then lastly, there's a weight-based systematic uncertainty where we, instead of using our default weight, which is just called weight, if you scroll further up, we want to replace those weights by other weights, and then we call this a systematic uncertainty as well. So let's update our config. Now we have systematic uncertainties included. And what we need to do is we need to create our histograms again. You see the output this time is longer. We create more histograms because we need new histograms corresponding to the systematic uncertainties that we have just defined. We can visualize, again, the output. This is a different type of visualization now that's specifically for systematic uncertainties. And you see here the two that we have defined, the one where we replace our nominal background modeling by a different, which is shown in black, by a different prediction, which is shown here in blue. And at the bottom is showing you the variations under our weight modeling systematic in this up and down direction. So this is useful to ensure we have defined our systematics correctly. And you can see if you change the systematics, how these plots will also be changing. With all our templates available, let's build a workspace out of this. Cabinetry does this with this workspace module. There's a build function, which you hand again the config, because the config includes all the structure of your model. We save it to disk here. This is optional. We could directly continue with this workspace dictionary instead. All right, so we have the model available, and it's time for statistical inference. To do that, we need two things. We need a probability density function, or a PDF, which we'll call model here in the following, and the data that we can fit this model to. There's a function to get that. And if you run this now here, you will see that there's a few different modifiers that PyHF creates for us, some which relate to these parameters that we have specified, our systematic uncertainties, and this signal normalization parameter that we want to measure. There's also a new thing, stat error, that enters here that you might not have expected. This describes the statistical uncertainties of your model prediction, and it's automatically included by Cabinetry. It's an important systematic uncertainty to include in practice, and it's done automatically for you, so you don't need to worry about it. So the model itself is our PDF. What is data? Data is just a list of numbers. If we look at it, you see the first 4 numbers here. These are the counts of data in our 4 bins. The remaining things are the so-called auxiliary data, which we don't have time to go through in any detail now. Check out the PyHF tutorial linked here to learn a bit more about this concept. It's quite important, and we need to pass this auxiliary data around, but unfortunately, there's no time to describe this in any detail here. So we have our model, we have our data. So what we can do is we can fit our model to data with this fit function in the Cabinetry fit module. This just runs a maximum likelihood estimate. We use Minui through the iMinui package to do the minimization. We see the result reported here. Everything looks okay. And then we see also our parameter values listed at the best fit parameter point where we have maximized our likelihood. The results are stored in this fit results object, and this object is a named tuple. And in fact, we can easily do some other things with it. So it has a few properties like .labels, .bestFit, .uncertainty to access the results from this fit. So here's a function that shows you how to access some of this to reproduce here the output of your best fit that was shown here in the log. And you can similarly go ahead and use these numbers here from the results to do your own kind of things that you may want to use them in. Instead of just using looking at an output, it's often much more helpful to visualize everything. And one thing that we typically visualize with such models is the so-called polls. So there's a function for this as well, where we pass in our fit results, and then we get back a plot like this. This plot shows us nuisance parameters with constraints and how far they have been so-called pulled away from their nominal value, which is 0 for these nuisance parameters. and how constrained they have been. Constraining here means the uncertainty, which is shown as this bar, becomes smaller than what it is before performing the fit. So our data was sort of sensitive to give us some constraining power over this nuisance parameter. Another thing that's very commonly looked at to understand the fit a bit better is correlations between different nuisance parameters. You can do that as well, of course. There's a pruning threshold that you can apply here to only include parameters that have a minimum correlation with other parameters and not look at those that don't matter too much. Now, how does our model look like after the fit to data? There's a function here that allows you to draw the distribution of the model just using information in the workspace. So both this model and the data comes from our workspace, comes from our fit model. We pass in the config here for some styling, but this is optional. If we run this, we get yield tables that shows us the counts for the different background and signal contributions and of data, including full systematic uncertainty. And there's a figure as well that is produced that shows us now the pre-fit situation before the fit has been performed, with quite large uncertainties shown here in this with these hashed lines. And we can visualize the same thing after the fit by calling the same function, visualize data underline MC, but passing in our fit results tuple here. If we do that now and we can compare the two figures, you see that this uncertainty has significantly reduced due to our fit, due to the correlations that have been determined by our fit, and also a bit the constraints that have been measured via our fit. And this is now the post-fit model, including full systematic uncertainties again here. There's a few other things that are available in Cabinetry, which we don't have much time to go into, but one thing you might be interested in practice is the so-called Asimov dataset. See this paper for some reference here that allows you to evaluate the expected performance of your model. We can obtain that via a function in this model under an utils module within Cabinetry. And then if you fit that data set, you see now suddenly all the parameters are either 1 or 0, which is sort of the defining feature of this Asimov data set. Going beyond just simple maximum likelihood estimates, Cabinetry includes interfaces for more calculations using PyHF to run the calculation internally, but wrapping everything up into an interface that reports to you all the things you care in practice about usually. You can calculate the discovery significance for our model fitted to data, and we get an expected significance of about 1 sigma and 1.8 sigma observed because we have a slight excess of signal in our example. Another thing you care about is parameter limits, which we've seen in the previous plot, in the previous talk, sorry. Here we do that by switching out our data. We just pass in a new list of data just to demonstrate that you can easily switch out data if you care about the limit for a different set of data, and then we calculate our limits. This uses brand bracketing to determine the points where this CLS quantity crosses 5%. This is the method that we're using here for the limit calculation. It does so for all the observed and expected limits, and it finally visualizes everything as a function of the signal strength, and it includes your observed and expected limits as well. And then one last thing I want to very briefly mention is how we can use Cabinetry to work with a more fully featured, more realistic full-scale atlas analysis. This is a search for electrovolcanoes linked here, available on HEP data through this link. We download it through PyHF, and we use one of the available signals also again through PyHF, and we save it to disk to have it available. There's a useful utility here, PyHF inspect, that we can use to have a look at what's included here. We see there's 8 different channels, 10 samples, 120 parameters. So now this is a model much larger than what we used previously. So this is a more realistic scale. Remember, before we had 1 channel with our toy model, 3 samples, and I don't know how many parameters, 8, 10, something like this. So this is a much bigger model now. We can still use Cabinetry to handle it. So one thing we need is we need to obtain the PDF and the data for our model. And with that available, we can visualize everything. So here now, again, we call the same function, visualize data MC. And we skip the yield table just because there's lots of different phase space regions and it will be very large. You see there's 8 different channels. So we get 8 different plots now. You can look through them afterwards. You see there's sort of signal regions and control regions with more events here in this example. And what we can do is, just as before, we can run again a maximum likelihood fit. Now this fit takes a few seconds because instead of having just the handful of parameters we had in our toy model, now we have something like 120 parameters. So this is understandably a bit slower to run, but it finishes within a few seconds still. When we run this fit, we will see all of our best fit parameter results. And this time, for 120 parameters, it will be a very long list. So it's actually very difficult to visually parse. You can scroll through the output here by yourself, and you'll see that there's just a long list of numbers. So it's much more useful now to visualize them. And here you really see the power of the visualization. When you see many of those parameters here that are neither constrained nor pulled, and then you see some parameters that might be a bit pulled, like the parameter down here, or some parameters that might be a bit constrained, like some of the parameters here, and then you can focus on those parameters, and visually they're very easy to spot. That's it for the notebook. There's an additional function here if you want to visualize the post-fit model. This takes a few seconds, so it's commented out here. And there's much more bonus material at the bottom if you're curious about extra things. But that, yeah, it concludes the main part of what I wanted to show you today. So thanks a lot for following along, and I'm happy to take questions now. I can switch over to Slido.
Yeah, go through Slido, thanks.
Yes, okay. Is there support for generating toy models and fitting to them? In Cabinetry right now, there's not an interface for this, but PyHF has an interface for toys. So at the moment, the way to do this is that you create your model, for example, with Cabinetry or otherwise, and then you use PyHF directly to sample your toys. So the nice thing about Cabinetry is that, I mean, there's no barrier with going back to PyHF. There's in fact an example further down in the notebook where you can go back and forth. So the objects that we handle at the inference stage, which is our PDF, what I call model here, and the data, those are exactly the same thing that PyHF handles as well. So instead of using Cabinetry to run a fit, you can just as well use PyHF to run a fit. And you will see that it's like slightly different with the options that you have available. But for the toy models, the way to do this right now would be directly to use PyHF. If there's things missing there that you would like to have packaged up in an interface, please get in touch, because I'm sure either the PyHF developers or like through Cabinetry, we would be happy to implement those to make it more user-friendly. Okay, currently I have columnar data in another format, Bokeh. Is there any way to use Cabinetry with that, or with pandas Dask root data frame in memory? Okay, great question. So at the moment, Cabinetry only reads root files through this uproot backend. This, however, like in the way everything is written, is not really that difficult of a requirement to circumvent. So the way things work is the main Cabinetry library includes the logic to determine which file do you need to look at to build the template histogram that you care about. At the moment, this backend with Uproot just reads root files. It should be fairly straightforward to add another backend that reads files in a different format and again makes the histogram out of that, because that's sort of completely decoupled from all the rest. In fact, you don't even need to import Uproot or whatever other dependency you might want to use to read Bokeh if you just use this sort of core functionality. So it's not there at the moment. I'm happy to have something like this included. And if you're interested in this, I mean, please get in touch. Everything sort of factors out, and that should make it quite easy. I should also mention we plan on using on supporting coffee. I mean, there's an experimental branch that allows this right now. I cannot comment on whether coffee already reads Bokeh or not. Maybe someone else can know, and we can follow up with Slack on this afterwards. But there is no strict restriction to root files. This is just an implementation detail right now because there's a finite amount of backends, and many people use root. So that's the that's just a reason. That's the reason for that. Sorry. Cabinetry is awesome. Thanks a lot, Matthew. Nice talk. You mentioned that Cabinetry is integrated with coffee. When do you expect to have it available? Okay, that's a very good question, and I will link to you on Slack afterwards some more details about this. In principle, the current integration could already be merged. I was hoping to improve it a bit, and the reason for that is mostly that to really take full advantage of coffee, we want to run as many things in parallel as possible. And that requires some slight refactoring that, unfortunately, before PyHEP didn't happen. There is a lot of potential to do some clever things that are requiring code that doesn't exist at the moment to use coffee really to its maximum capabilities. And this GitHub issue on this GitHub discussion on coffee that I'll link to you afterwards goes into some detail there. But yeah, I'm expecting that coffee itself, I mean, we should have this available within the next month or so. A nicer version where we can really use coffee to its largest capabilities might take a bit longer because there's some more work to be done there. Okay, thanks. Another question. Does it handle multi-dimensional histograms and PDFs? No. At the moment, everything is one-dimensional, and this is a restriction of the Hist Factory model itself that we're following. There are ideas of going to some sort of extension of a Hist Factory model to have some Hist Factory version 2.0 or something like that, where we could relax these sort of requirements. At the moment, this is a hard requirement. If you have multi-dimensional distributions, one thing you can do is, if you have, for example, a two-dimensional distribution, you can break this down into multiple one-dimensional distributions and fit those. Because in the end, it doesn't matter so much whether bins are adjacent to each other or not, because you just look at each bin individually. It does matter slightly if you do things like smoothing, but otherwise it doesn't. So it's currently a limitation of the model that we don't go to multiple dimensions. Yes.
Alex, what about to move discussion to Slack? So all these questions will be posted in Slack in which channel? Ben, could you remind? Fitting, probably. Yeah. Okay.
Yeah, that's right. Fitting in statistics.
Thanks.
Okay. Yeah, sounds good.
So yeah, thank you so much for a nice talk, and you see how many questions. It's great. For us all, I would propose to go for the break, and yeah, we will be back basically in 30 minutes.
Since we'll be starting in a couple minutes, I'd like to check my microphone.
We could hear you.
Okay. And I heard you too, although I'll be turning up the volume.
Did you say I'm quiet, Jim? Is that what?
Was that?
Did you say that I was quiet? Is that what you?
Oh, I turned up my volume.
Oh, okay. Fine.
Hi everyone. So I think it's normally time to get back to the second session of today. So we will have a tutorial on HEP specific packages, Uproot and Uproot, and then a few lightning talks to finalize. So please go ahead when you're ready, Jim.
Okay. So I'm just going to share this whole desktop. And I'll be keeping the Slido up so I can be answering questions as we go along. Now, the very first thing before we get into anything, I want to call people's attention to this in Slack under #announcements. Eamon is looking for people to be on a panel for SciPy Birds of a Feather for HEP. SciPy is the main scientific computing in Python conference, and it is next week. So if you're interested in that, there's a section here where you can join and talk about it. Okay, so I just wanted to point this out. All right, so now for the tutorial itself, I'm going to ask that you follow along with this, because there are going to be some questions in the middle, and I really want to encourage interactivity on this. So from the Indico site, there's a link to the notebooks on GitHub that I'll be using for this. That looks like this GitHub site, and there's a giant button, Launch Binder. Please, everyone, do this. Please, everyone, click the Launch Binder button, so that you'll have a copy of this going. And you'll be able to evaluate this along with me, and also try different things and ask me about those different things. The way that I view these tutorials is I'm like I'm like a tour guide, giving you a tour of some ancient ruins or something, and I have a set itinerary just to get us started, but any questions that you have along the way about what's this, what's that, what happens if I do this, what happens if I do that, is more important than the planned itinerary. This is here to, give you a chance to ask about these things. So please do launch that binder so that you can be running this. without having to install it on your computer, because everybody's computer is different and we can't deal with the installation issues in only 1 hour tutorial. Okay,
Jim?
or if you have it running on your computer anyway, go for it.
Jim, a quick question.
Yeah.
Given the way you're going to run the show here, shall we give only 5 minutes at the end, and you take, say, 55 minutes overall for the whole thing? Is that a good compromise?
Well, toward the end, I made sure to include a little bit more material than we can cover.
Mhm.
So toward the end, it's going to be a little bit of a soft ending.
Okay.
I hope that there will be questions throughout, and then I'll go until I run out of time.
Okay, then I don't bother you until 1 minute before. All right.
Sure, great. Okay. So, yeah, so launch that binder button. And you should get something that looks like this, and I'll just get going. All right, so for the uproot and awkward array tutorial, I'd like to start actually with not uproot or awkward array. I'd like to start with showing the same analysis several different ways, 3 root ways and 1 uproot awkward array way. And actually the point of this is not compare and contrast like good and bad, but compare and contrast like what do you get from this and what do you get from that? Because things are always best when used together. But mainly to show, why are we doing this? What is different about it? So let's start with, okay, we're going to make a z-peak. It's like the hello world of high energy physics. So in root, first we import a bunch of libraries. We open the file, and then the PyRoot way of going about it, which is not the root way, I should say, but the PyRoot for loop way of going about it is the sort of the most straightforward way to do it, is to, write a for loop over the events, cut out the events you're not interested in, and then for the events that you are interested in, compute and fill a histogram that was defined outside of the loop. Okay, so that finished after 24 seconds, and we got ourselves a z-peak and some low energy stuff, dimuons. Okay, that was straightforward, but for this particular problem, it didn't have to take 24 seconds. It could run a lot faster than that, and really this is because we're doing Python stuff on the scale of the number of events, and number of events is a very large. Here it's 123,000. So the traditional way to solve that is to mix in some C++, because C++ is much faster than Python when writing for loops. So here is the same analysis in C++. Now you notice it's all red, and that's because this is all inside of a string. And this is being passed to rootginterpreter declare. So we can declare a function, all C++ syntax. In fact, this is like old-fashioned C++. I'll be getting to our data frame in a moment. And root, and actually this is PyRoot, but it's being using PyRoot in a very different way. Having defined that function, we can now call it from Python. This compute is now defined on root, so we can say root.compute, and we can run that thing, and it is way faster than 24 seconds. You can run it a bunch of times, and caching has an effect, but produces the same plot some 500 times faster, 700 times faster, something like that. Okay. And that's a big enough factor to matter. If it was like 20% faster, then, well, do what's convenient. But if it's 500 times faster, that's the difference between a coffee break and overnight. So now that is old-fashioned C++. The new way to do this is using our data frame, which allows you to leverage Python quite a bit more for the organization of the analysis. So the modern way to do it is to build workflows that are like pipelines. So our data frame has a source df, and then you make these little nodes by assignment. So df2 mu is when you take df and apply a filter to it. dfos is when you take df2 mu and apply a filter to it. So you make this chain of things, and the chain doesn't have to be a linear chain, it can split. And everything that has to be fast, that runs over many events, are inside these quoted strings, and these quoted strings are C++. So you're writing C++ to do things fast, but you can organize your analysis, build the workflow chain in Python. So you get to use the bookkeeping of Python with the speed of C++, and that's very nice. When you do this, and here I decided to use as NumPy as the action that drives the calculation, because this all was just setting up the workflow. Now we run this, get an array, and it's still quite a bit faster than PyRoot. There is some kind of caching going on, so that it's faster if you run it again. And again, we get orders of magnitude to make the same plots. Okay, so that was 3 ways to do it in Root. Now, a workflow that's natural to uproot an awkward array is for you to not write any C++. That's the idea, is that you do everything in Python. You're not writing for loops in Python. All of the loops are happening in compiled code, but you don't write that code. You're piecing it together from smaller parts. So here we'll import some stuff, load the events, and I'm going to just show this T-tree. This is sort of like a first look. It's kind of a text-based T-browser, I suppose, to find out what are all the types of branches in this, what are the kinds of things that we can plot. The way that we do things is quite different from our data frame. We first extract arrays as one step. The first step is just get the arrays out. And now this muons is an array. And it's a structured array that has things like fields inside of it. And then when we want to do any kind of analysis, that means making new arrays from this array. So a cut, for instance, is an array. It's an array of Booleans that we construct by performing computations on this muon. So we take muon's charge, we ask how many of them there are, we require them to be at least 2. We require the sum of those charges to be equal to 0, adding over the 2. That's the cut we want to apply. And then applying cuts is slicing. And we can, at the same time as cut slicing, we can also be slicing to take out the first element or the second element and break them into 2 different arrays. So now mu1 is all the firsts, mu2 is all the seconds. We can use Pythonic histogramming. This hist library is great. This just created an empty histogram, and this filled the histogram with this formula. I'm computing with NumPy. And this Jupyter view, this little thing only comes up in Jupyter, and it's kind of a quick and dirty plot. If you want real plotting, it has backends to Matplotlib, and it could presumably have backends to other favorite plotting packages. So okay. So yeah, now pulling all that stuff together into a single slide, into a single cell. This is again on the order of, it's orders of magnitude faster than the PyRoot for loop. So now we have the cake and eating it too. We're doing everything in Python, but we're not hampered by the speed of Python, and we're using the same kinds of techniques that NumPy and Pandas users use. So, okay. As a reminder, everybody's got access to Slido. So if you have any questions, just put them there. Really, anything that you ask there, we'll all see it. You can be anonymous. and I'll ask your questions as we go along. That anyway was sort of the intro part. So I'm mentioning the question box now because I'm moving on to focus on Uproot in particular. All right. So now, so some more sort of grand view of all this is that Uproot is not a framework. It only does root IO, and we really wanted to avoid scope creep in Uproot. So anything that smacks of, making histograms or performing computations, we wanted to make sure that that was not part of Uproot, because we didn't want, there to be like, we didn't want Uproot to become, a new like monolith. So Uproot only does the root IO. Awkward Array only handles array manipulation. So Awkward Array doesn't know anything about root, for instance. Hist only does histograms, etc. So it's all sort of a part of this complete breakfast. The idea is that all of these little packages each fit a different niche and they each do their own things. In case you're not aware, Uproot is not a thing that is calling root in order to do things. It is a separate implementation, and that makes it pip installable. So you can say pip install Uproot, whereas it would be difficult to include the C++ code base in pip, the C++ code base of root in pip, although it is quite possible to include it in Conda. And so if you use, so a little advertisement for all the good work that Chris and others have been doing on CondaForge, you can Conda install root, and that's a big deal because it'll be linked to your Python, and that's great. But anyway, Uproot is a small separate package, and it uses all these other Python packages in order to do all the other things like make histograms and manipulate arrays and such. And it uses standard Python components whenever possible. Here's the documentation. So all these functions are documented. And now let's get into actually exploring a root file. So some terminology before we get into it. Root file contains in it directories, and you can navigate around in the different directories kind of like you can in a file system. In fact, there's a sense in which a root file is a little tiny file system and has to deal with the things that file systems have to deal with, like fragmentation and such. The objects, anything that inherits from T object, can be placed in directories as standalone objects. But mostly we're using T-trees, and T-tree is one particular kind of standalone object that has a lot of substructure. T-tree has these T branches, and these are the named columns that you're usually interested in. I want the PT, the eta, and the phi, but I don't care about the other stuff. These T branches are broken into a number of T baskets, and that's a detail that you might or might not get into. T baskets are just chunks of the data, like the first 50 events, the second 50 events, the third 50 events. The only reason that you're likely to get into T baskets is if your T baskets are too small and they are ruining your read performance. So that's the name of that in case you need to get into that. Here we'll be living on the surface and just talking about T trees and T branches. So actually, before we even get into T trees, let's just look at some standalone objects. So here's a file with a bunch of histograms in it. When you open something in Uproot, be aware that you are getting the directory objects. So go back to this diagram. You're getting this, not this. There's one T file for the whole file, but then you can have lots of nested T directories. And so you're given the T directory because that is what you need in order to find, more stuff inside the T directory. Yes. Directories inside directories. Huh? Okay. Directories inside directories. but the T file has some just sort of global file information that you want to get into if you are interested in the compression of the file or something such like that. Now, these T directories, they act kind of like Python dictionaries. So here you see I pulled out a nested directory, okay, and by using dict-like syntax, and there are keys, values, items, and a new one, class names, for looking at all of them. Is there any limit in the size of data that that Uproot can handle? None other than the memory you have available on the machine. So no in principle limit, but if Python runs out of memory, Python runs out of memory. So the unlike a normal dictionary, these keys, values, items, and class names have extra arguments that you can use to refine your search. And you can use that to like get a bunch of histograms that match a naming convention, for instance. When I tried Uproot on large data sets, I was not able to make it work nicely. With small, it's fine. Best practices. Okay, so the best practices for problems with memory is to try to avoid reading too much. So for instance, in these keys, values, items, and class names, values and items will read data out of the file, because here you have so histogram.keys only needs to find the names of all of the objects in there, so it's not doing too much reading. But if I ask for items, that has just read every single histogram in the entire file, and all of that reading could be a problem. More likely running out of memory could be when we're doing the analogous thing with a T-tree. If we're going to just read all branches in the T-tree just by default by saying ttree.arrays, it'll try to read everything, and you might not have memory for that. Does Uproot not include any of root? It's just an interface. That is correct. Uproot does not include any root. This diagram says it all. This is what everything is built on. So Uproot is an independent implementation. So it just reads the root files directly, you know, as files on disk. Okay. Right, so there's a lot of histograms here. Most of the histograms and graphs can be converted into types of other Python libraries, and this is a point where we actually just want to expand this. So we have some links, and we'd like to make more links in the future, and this is a good place actually to get involved, because writing these functions is not too onerous if you know the libraries involved. So for instance, I pull out this histogram, and this is a th1d. We have things like to numpy that will give like what this would be if it had come from numpy.histogram, or to hist to give you one of these hist objects. And since that's got this in Jupyter mini display, that's a good way for browsing around all of these histograms. So using the things that I was just talking about, the fact that the keys, values, items, and class names, they have these filter by name, filter by class name, hint, arguments, and you can click on these links to get to the documentation to get more information about how to do this. With that. 3-minute exercise starting now. In your binder, from here, from this point, put some extra stuff in order to pull out the one and only 2-dimensional histogram and plot it. Let me say plot it with matplotlib. and that's 3 minutes. It's 9:52, so for me, so 9:55. I'll just hang around while you work on this exercise, and let me, I will clear this. Any other questions while doing the exercise are fair game? Meanwhile, I'll set up a poll. Okay. I'll get those questions in. So this is the poll. Meanwhile, I'll go to these questions. What about this issue? Well, okay. It's an active issue. Take a look at that in a moment, and I'll answer the other one in the meantime. Is Uproot implemented in pure Python, or does it? Uproot is implemented in pure Python. And of course, in the same sense as PyHF, where we of course use libraries that have compiled parts, most especially NumPy, but also awkward array. None of these are actually Python. Fields of struct interpreted with a type. So this is the issue. Fields of struct interpreted with a type of siblings. Okay. Oh, if it's member-wise splitting, then that's a not yet handled part of root. And I'll get to, actually, I've got a Venn diagram a little bit further on what can we read and what can't we read. And actually there are, and there's been a lot of discussion on this issue. And if you ever come across member-wise splitting, actually not just issues, but also pull requests. Member-wise splitting is a frontier part of Uproot. Being able to read data that's from a root perspective, it's an internal detail. You don't see the difference. But it's serialized in a different way. And so it needs specialized code in order to deal with it. And we have several efforts actually ongoing to try to deal with member-wise splitting. Although if the question is, why has this issue not been resolved yet, and it was from February, actually my main priority is adding the ability to write files in Uproot 4. This is long overdue. And so that'll go before member-wise splitting. Okay. And oh, we're at time. Okay, so the polls. All right, so only 5 people have been trying this. Really, all of you are not following on Binder and trying things out and either successful or not successful. Okay. Okay. So I see that when I ask the question, I get a lot more no's, which is just saying that, yeah, so I guess you were shy about saying that, that it didn't work. Okay. All right, so what I'll do here is I'll show sort of a walkthrough of how that works. So here we're looking for the 2-dimensional histogram. Let's start by, and since for the histogram to be 1-dimensional or 2-dimensional, that's a class name thing. So one of the early things you probably want to do when you're just opening up a file that you're unfamiliar with is to look at the class names. This doesn't read any objects. This gets all the names of things that you can open and their classes. So some things are T directories, some things are th1d, th1d, th1d. There's a lot of these th1ds. This actually came from the run 1 Higgs 2 for leptons analysis. So these are actually real plots used for physics. And one thing that you could do is just scan this by eye and look for the th2d, which I might be able to do, might not be able to do, because there's a lot of th1ds in here. And I didn't see it off the bat. But here I'm going to be using some root knowledge. I know that two-dimensional histograms are th2d, or actually th2 whatever. So one thing that I could do is search through all of these. How about key value for key value in if value is th2d. I could search for that. That returns a dictionary items. Could search for it that way. And so if it's exactly th2d, could eventually find it by writing this big long list comprehension. But this is the sort of thing that filter class name does. Or if you're not so sure that it's th2d and you think it might be th2 something else, like th2f or th2 whatever, you can use globs and such. So this is sort of an introduction to, like, this is how you search around. Okay, and then having found something like this, now we can use values instead of class names, and that is the histogram object. Sorry about the siren in the background. It's Tuesday at 10 a.m. So that pulls out the one and only th2d. There's its histogram, and then to plot it in matplotlib, the hist function for that is plot. Okay. So I'm going to switch this back to the Q&A. That was unnecessarily difficult. Read-only directories should have a rich show method with highlighting entries and one. Okay, that's interesting. So this is a good point for if you want higher level conveniences on this. It'd be great if you contributed them. That's actually a good candidate for the sort of thing where community feedback would be great. Because as you can see from the the member-wise issue, there's a lot of effort going into just getting any root data out at all. So if you'd like high-level conveniences, I would really like to encourage the community to add these sorts of things. Is there a grand collaboration such as CERN? One could just use Uproot to perform the entire analysis. There's, in principle, yeah, you can do analyses with Uproot, and quite a few analyses are being done with just Uproot. I'm not sure what the grand collaboration about CERN is, but so with that, with the yeah, you can do whole analyses. Now let's get to some limitations. Like, can Uproot read my data? And this is where we were just talking about with a member-wise. We should be aware that the set of all objects in all root files is very broad. Over the last few decades, you know, a lot of root files have been made in a lot of very different kinds of ways. And the root code is necessarily complex in order to be able to handle all those different cases, of which there are many. And even then, of all the things that have been put in files whose extension is .rot, not everything can be read by root itself. And I guess those are by definition invalid root files by definition. But then what Uproot can read is some subset of that, and it's a growing subset. We're trying to add more capabilities as time goes on, but it's a subset. And then this thing where the histograms had special behaviors for knowing how to turn itself into a hist or knowing how to turn itself into NumPy, this is even a subset of what Uproot can read. Okay, so question, Uproot could read the somewhat new rich protocol. Oh, again, this is Henry's answer to the previous question about pretty printing stuff. That would be super cool. That would be super cool, by the way, yes. But it's something that we would like to see contributed, because actually you wouldn't go deep into Uproot's internals. It is the sort of thing that a motivated user could do with some Python knowledge and some knowledge of rich, in fact. So here are some analysis specific classes. Hist was in this magenta. I'm going to talk about something in the orange now. Things that Uproot can read, but Uproot doesn't recognize. So this file actually came up because of a bug report a long time ago. Was from IceCube doing analysis of supernovae. And the class names, actually, instead of looking at the keys, let's look at the class names. The class names are user-defined classes. These are classes that were defined by IceCube, someone in IceCube, to do this analysis. And so we can recognize that it has that class. We don't know much about the class, but root includes the information about how to deserialize it. So this class contains all of these things that are based on the more simple types, integers and pointers and such. So that means because we have this information supplied in the root file, this IceCube data that we've never heard of, we're able to read it and look at its data members, including like standard maps and stuff like that. And so this is how you could do a data analysis even with some custom classes, assuming they're not like member-wise split or something like that. So generally, when you want to find out if Uproot can handle something, it's just first go and try it. And if it can't, raise an issue and we'll try to handle it. Okay, so that was all the navigating around through Uproot, other than T-trees, but T-trees are kind of what you're here for. T-trees are the main thing that we put into root files. So now let's look into navigating T-trees. So here's a file that contains just one T-tree. And when you enter into this, there is a show method. And maybe actually this is what you're looking for the file, in addition to just the file.keys and values and items, to have something like show to pretty print it. In fact, maybe this would be nice and rich as well. So this is what you get by just showing, and from a lot of feedback, I know that people use the show quite a bit. But when there is a convenient method like this, sometimes people can not find out about the fact that there are more low-level methods to get the data directly. Like they'll want to have the names of the branches, but if you only know show, then you start parsing this and it gets pretty bad. I want you to know that you can use keys, type names, and items to get at all the data that's up there in a more programmatic way, so you can integrate this into your scripts. Some time ago, I was able to use PyRoot to do customization of the root file made by experts. Am I limited to standard root formats? You mean, I think you might have meant unable to use Uproot due to some customization of the root file. There are customizations of root files that will prevent Uproot from being able to read it, custom streamers. You are not limited to standard root formats like NanoAOD because this set of things that Uproot can read is not limited to, standards like NanoAOD, but what falls into this and what falls out of this can be very subtle. So if experts add something that knocks it out of this group, then that's something we want to know about. Okay. So then, in order to do any kind of analysis with the T-tree data, we want to get the data out as arrays. And the simplest way to do that is to get a T-branch object and ask for its array. That is the most basic array access. Some important parameters that I'll let you explore on your own by going to the documentation. Entry start and stop determines how much you read. And you can also set the library. So here we limit reading to 5, and this is actually limiting the reading. So if you have a data that's too large and you can't read it into memory, try using entry start and stop so that you're not reading as much. We can get a NumPy array instead of an awkward array by saying the library is NumPy, or pandas series by saying that the library is pandas. And these are just abbreviations. You can use the full name. Now, the single array is the basic interface, but you're also able to read many arrays at once, which again, if you're not careful with that, you can run out of memory. But you can read many arrays at once, and that's useful if you want to minimize the number of round trips with like a remote. You've got all your data in XRD, and every time Uproot asks for something, there's a round trip latency involved in that. So if you want to get all of the arrays with a single request, use the ttree.arrays method. And what that will return is some kind of a group. The group depends on the library. So if library is NumPy, then arrays returns a dict dictionary of from the name of the branch to the array. And these are all NumPy arrays. If the library is pandas, a group is a data frame. So if you are looking for the pandas way is ttree arrays libraries pandas. I'll also know you can set the library. You can set the library globally, so you don't have to keep saying that. So default library equals PD or something. The first argument can be used to extract T branches by name. All right, so question, is there an analog of T-tree index for adding a friend tree? Actually, the friend tree information with the T-tree index is part of the frontier. It's data that we can see it there, and we've been skipping over it. If there's enough interest in doing T-tree indexes, we can extract that information. I know where it is. And actually, that would be a good thing to put in the pandas index, because then you can do a pandas data frame join for 2 friend trees. And that would be a really good way to use pandas to do friend trees. Oh, just random thought. Okay, why would we pick pandas over NumPy over awkward for your data? What's the, okay. NumPy for speed if your data are simple, and we'll be talking about when you need awkward array for the complexity. But other than speed versus complex data types, that's the choice between NumPy and awkward. Pandas is if you want to use all the Pandas functionality. Pandas is slower than NumPy for sure, and then awkward array in some situations haven't done like all the different cases. And there are also some things you can't express with Pandas. But if you're going to do a Pandas analysis and you have a lot of Pandas functions you want to be using, then yeah, turn it into Pandas. And actually, I'm going to be using Pandas a lot in these examples because it makes a pretty table, and it's in Jupyter. So the thing that I'm using this pretty table in Jupyter to show is that what goes here in the first argument, although we could put the names of the branches that we wanted, that worked because the name of branches are just simple expressions that when computed give the branches. What goes here actually are full expressions. So we can make a table with column titles like that. This was to support aliases. Aliases are usually burned into a T-tree, but you can define aliases on the spot. And one of the nice things that you might want to use that for is to give your Pandas columns meaningful names. So this is the aliases. Actually, I should maybe make this more explicit. Aliases. And these expressions will be used in evaluating this. Can we still use NumPy or Pandas if we have jagged arrays? Not really, or sort of. And that's the first thing that I'll get into about awkward array, and it might be the last thing I get into in this tutorial. So speeding on to that question, what is the expression engine for the aliases? Very, very good question. It's pluginable, and the only plugin is Python. So these expressions are all being evaluated in Python. There's not any computational advantage to doing this calculation inside of these strings, although it did make a pretty slick way to get a Pandas data frame in a one-liner. But the idea is that this Python engine, we'd like it to be swappable with an implementation of the T-tree draw syntax in Python. And there's a package called Formulate that does this, but it needs some dusting off. And that's the kind of thing that we'd like to see there. We'd like to see these be T-tree draw expressions. All right, I'm not going to clear this because I want to keep this question around. But before leaving this, I want to make this point that since these are expressions, you want to be careful with branch names that have slashes in them, or any attempts to get wildcard paths with star, because slash is division and star is multiplication. Even if this were T-tree draw syntax, that would be a problem. So if you want to be selecting T branches by some sort of name filter, such as these glob patterns, use the filter name, filter type name, filter branch in the arrays in order to get that. And if you have a naming convention on your arrays like nano AOD, that can be super useful. And also note that these are exactly the same interfaces for keys and type names. So you can debug your filter without reading data and then apply it to arrays and read the data. Is it possible to cut variables we're not reading? It is possible to put a cut here, I should say. It's using the same expression, well, same expressions that are not being shown here. Px1 greater than 0, let's say. Bother. I need a comma. Yeah, so now the px1s are all positive. Although this is really just using Python. This is doing the same thing as if you had extracted these arrays and applied that cut after the fact. So to answer the question of can you cut variables without reading them? No, not technically no, but logically no. You have to read the data in order to cut on it because you have to know the values of the quantities in order to cut them. So any kind of cut will involve a read. Putting the cut here in this sort of convenient syntax is hiding the fact that it is in fact reading this, but it has to read it in order to know which px's are greater than 0 in order to apply the cut. Getting arrays as manageable chunks with iterate and collections of files. I'm going to leave that on your own because I want to get to the jagged arrays because there's 10 minutes left. So this is the next really important point, that the reason I wanted to keep this question around. Okay, and as I recently learned through digging source code that Pandas' query of valid engines support backtick escaping them containing bad characters. And maybe, okay, so maybe we want to start using backticks in our Python in order to do the same thing as Pandas. So that would be cool. We actually, those strings, those Python strings, we evaluate their abstract syntax tree, their AST, before sending them on. So we would be able to do things like that. Although backticks, that might be a syntax change, but that's all doable. You can use uproots to write a new branch to an existing T tree from Pandas data frame. That is why it's such a high priority to add file writing to Uproot, because currently Uproot 4 cannot write files. And that's exactly why we want to add that. Okay, so now in my 10 minutes left, I'm going to talk about jagged arrays. Oops. And this is just moving, this just got uploaded. Okay, I'm going to archive these in order to talk about jagged arrays. Okay, so I deliberately showed examples where the data were simple, where there was, where in the previous example, all of the type names had been just like an integer or a float per event. Here, it's quite common to get, and such as this one, net PT. The missing energy in each event is just one number per event. So we can get a NumPy array of that, no problem, and we can slice it as a NumPy array, no problem. Okay, but a lot of our data can't be expressed that way. We have a lot of data that's like this, muon PT, where we have a variable number of muons in every event. This first one had no muons, the second event had 2 muons, and so there's 2 PT values, and so on. If we were to look at just the first 20 events with this entry stop, and now taking that jagged array and say toList, turn it into Python lists, so we can really examine it, but you want to limit to only like 20 events when you do that. We see that the data looks like this. There are some events, because this is Higgs to 4 muons, so Higgs to 4 leptons, some of them have 4 muons in them. And so that's what these types are. Float arrays. In C++, this would be an array. In Awkward, it's known as a jagged array. That's a CS term for arrays that can have variable number of components. So it is possible to do that in NumPy. I want to show that the library equals NP is not broken. It is capable of putting all that stuff into a NumPy array, but this is an array of NumPy arrays. And that's because you can put Python objects in NumPy arrays, and I do not recommend this because putting Python objects into a NumPy array turns that NumPy array into an inflexible list. You don't get any of the performance advantages if it's a NumPy array of Python objects. And in addition to the lack of performance advantages, let's say that we wanted to say, take all events from the first dimension, the first dimension is events, and take up to the first muon. So we want to see the 0th, the first muon in each event if it exists, and nothing if it doesn't exist. If it's an awkward array, you can express slices like that. No problem. Okay, the first one had 0 muons, so the inner slice took out nothing. The second one had 2 muons, So the inner slice took the first one. And some of these had 4, and they'll be just taking the first one. But when you try to do that in NumPy, it's an error because these things in the NumPy array is not a second dimension of the array. It is random Python objects that NumPy doesn't know anything about. Random Python objects that happen to be NumPy arrays, but nevertheless, NumPy does not know anything about them. If you had such a thing, you would be forced to write a loop in Python, but that's not recommended because it's non-idiomatic and slow. And now, as of NumPy 20, they start warning you about it. They say, if you're really going to do this, explicitly say dtype is object. So how come NumPy doesn't support jagged arrays? And could this eventually be included? Actually, the scientific Python community hasn't really been I can really count on one hand the number of projects that have attempted to deal with jagged arrays. They're hard to come by. And the first one is 5 years old and abandoned. So jaggedness is kind of a frontier thing. In high-energy physics, we deal with variable length nested data all the time, but only recently have started using Python and NumPy and such. Python and NumPy have been dealing with arrays for a long time, but only recently have started dealing with jagged arrays. So that's why it's not in NumPy, and NumPy is kind of too old of a library to have that kind of a fundamental jump. Although, you know, if they integrated awkward array into NumPy, I would be very happy. Is it better intuitively to understand, to extend attribute positional indexing or commutative and what? Well, okay, so this question is kind of beyond the scope of what I've introduced so far. By attribute and positional indexing, we're talking about indexes that are strings versus, and therefore fields of a file name, and indexes that are integers, in other words, like this integer. And I haven't talked about enough yet in order to really answer this question. So I'll answer the question in Slack offline. Can awkward arrays be converted into ragged tensors in TensorFlow? I think that would be awesome, actually. I've been looking at TensorFlow's ragged tensors for a while, and I think that two underscore TF from underscore TF functions would be great. And if there's enough use cases for it, that would promote its development. So how do operations on TensorFlow ragged tensors compare? Awkward array is much more general. Ragged tensors are only the jagged part. And the jagged part is being used here as motivation, but it's kind of the foot in the door to, we want full data types. And jagged arrays or arrays of lists is only the beginning of full data types. I'm going to jump ahead to what do I mean by full data types? This is what I mean by full data types. So in general, awkward array data types T, the type that any array can have, can be numbers, booleans, date times, etc., variable length and fixed length lists of T, and so that includes lists of lists of lists of lists, records with named or unnamed, in other words, tuple fields of type T1, T2, and that's where this question was getting at. Missing values, T or none, such as the examples that Henry was showing in Python with option type, and also heterogeneous types, although that's kind of the bleeding edge, that you can have a data whose type is either T1 or T2 or T3 or whatever. And so this data model is considerably more general than ragged tensors, but it would be cool to have converter functions so you can get plain old jagged arrays right into TensorFlow. And before leaving this, I want to say that pandas can kind of do this too. And I have a sample here with pandas. And by the way, we just experienced some pandas slowdown. If you notice how much slower that loaded. So here we're taking all of the branches that start with muon. And since all of them have the same jagged structure, they all have the same number of sub-entries per entry, we're able to make an index for this table that reflects that, that nestedness. And you can use this index with some pandas functions in order to do jagged array things in pandas. Now I'm going to show some of the limitations of that. So let's say that we want to include in the same data frame, actually, some variables that are, so the met PT and met phi, there's one per event, and the muon PT, muon eta, muon phi, there's several per event. That having the whole data frame's index be based on this muon's jaggedness means that the non-jagged things have to be duplicated or removed. So any events with no muons, we don't see what the net is in order to get it in the same data frame. And then even more so if you want to include generator level generator level in that same, since this has a variable number of objects per event and this has a different variable number of objects per event, there's no way that those two can be in the same data frame unless you do some kind of squashing. And you are allowed to take these two data frames and squash them how you like. So it's 10:30. I can continue answering questions on the on Slack, maybe just this last one, and quickly comment on the timescale getting awkward in RDF. This isn't awkward, and our data frame interoperability, so you can take an awkward array, send it into our data frame, take an R data frame, send it into an awkward array, is a project I very much want to do, but it has to sit after uproot file writing. At least uproot file writing has to happen first. So we're talking about some months in the future. Okay, since I've answered these, I'm going to clear the board now for any last minute questions. No last minute questions. We have to go to Slack because the next talk is up. By the way, there's tons more material on doing some simple and quite complex operations with awkward array involving a lot of examples with Numba. So if you want to learn about Numba, this is a good place to do it offline in this. Okay.
Thanks very much, Jim. Yeah, that does indeed a lot of material. you could stay here the whole day probably if you wanted to discuss all the functionality available. But that's good. I mean, the people then have time to play around it. This is how it works. Thanks again. So we
and let's pay attention to the next speaker.
Yep. Hi, Ariana. I see you are connected already. Oh, I can see you. You should be able to share. So we're now going to have a series of 3 lightning talks. So remember that roughly it's 8+2, right? So you allow yourself a little bit of time for a couple of questions. Yeah. Please go ahead.
Sure. Thank you, Eduardo. Hello, everyone. Today, I'm going to be talking about a new interface for the C++ FastJet library. And for those who don't know, the C++ library called FastJet is used to perform jet finding on particle data. And there are several Python interfaces currently available for it, but there are some shortcomings that we wanted to address. So we came up with this new interface. What this interface does is uses several new PyHEP technologies that have come up recently, some of which that you heard about in the last talk, and we use that to address these issues really. So what this means is that now soon you'll be able to pip install FastJet. So this will be the first time that the official FastJet bindings will be available through PyPy. Also, this package comes with all the bells and whistles of the C++ version of FastJet. So that means that all the plugins, all the algorithms, and the CGAL support is enabled as well. And also, we intend to add FJ contrib in the future as well, but that will have to come at a later date because of the technical constraints that we face. So now let's move on to PyJet. PyJet is a popular Python package for using FastJet with NumPy. It's currently available under PyHEP, and it uses NumPy arrays to provide event level vectorization. However, it has two problems. The first is that it takes multiple function calls to process multiple events. And the second is that it uses FJ core. That's the header version of the C++ library of FastJet. And the problem is that if you compare the core library and the main library and FJ core, the results are different. So that is a problem. So here's an example run of PyJet. What I'm doing here is simply importing the test data, putting it into the cluster class, and extracting 3 exclusive jets. As you can see, these are 3 pseudo jets that it produced. This is sort of how the PyJet interface works, and this is what's available under PyHF now. So the 2 problems that I mentioned, how does the new interface solve them? Well, for the first problem, we use awkward arrays. You must have heard about it just now, actually. Awkward array is a Python library used to handle jagged arrays, really, and that helps us in handling multi-event cases here. Also, to solve the second problem, we have used the full FastJet C++ library. We're not using the header version called FJ code. We're putting the full FastJet C++ library on the Python wheel. So in this image here, you can see sort of describing what really happens. This classic interface here represents really the C++ interface and a Python interface that is available with the C++ library. And as you can see, these small chunks are really particles, and individual particles are used as a Python object, and then they're put together in a list, and then the jet finding is performed. However, in PyJet, what you find is that the whole event is treated as one Python object, which what I mean to say is that there is event level vectorization. But as you move down the axis, you see this new interface that we are making, it provides multi-level vectorization. So the multiple events can now be treated as a single Python object. So talking about this new FastJet interface, there are really 2 interfaces within this interface. One is the classic interface, which was taken from the C++ library, which is generated by the C++ library, and you can compile it using that. And the next one, new one, is the vectorized interface, which uses awkward to really handle the data. So I'll give short examples of both kinds of interfaces here. The first is obviously the classic interface. It's written in Swig, which is a tool used to bind C++ classes and functions in Python. And you can, as I mentioned before, download and compile it from the C++ version of FastJet yourself. We've put it on the wheel because it was easy enough to put it there, and it provides an alternative to people who want to use such an interface. So I'll just run the cells here. And as you can see, it works very similarly to how the C++ version works. Here's a jet definition that I'm defining. Here is a list of pseudojets, and then I'm putting them into the cluster sequence class and extracting inclusive jets from that. Very straightforward. And so what I want you to notice here is that 2 things. Well, the first is that it does things one event at a time. And second is that things are done almost similarly to how they're done in C++, which is using a jet definition and making a list of pseudojets. Well, in the case of C++, it was a vector of pseudojets, but yeah. So what's different in the new vectorized interface? Well, first thing is that it uses awkward arrays, and the inputs are primarily awkward arrays, and also the outputs. Wherever you need an output of, wherever the output is an array, we use awkward arrays. And the Python classic interface and the awkward interface also have a big overlap. So that means that we have reused some clustering specification classes for this as well. I'll show you what that means in a minute. Here's an example of awkward array. There are multiple events in this, as you can see. The first event has 3 particles, the second has none, the third has 4 particles, and the last has 1 particle. So running this cell, and now we go to the cluster sequence class. So as you will notice here, I'm using the same cluster sequence class and the same jet definition instance. All that has changed is the data type of the input array. which is now an awkward array. So I'll run this here, and you can see the inclusive jets are extracted just as easily. But this time they're an awkward array because this was a multi-event case. Now, if you look at the type here, what this says is that there are 4 events, each with a variable number of jets, and each jet is a specific record type. Same when you go to extract the constituents, what happens is you get awkward arrays, but this time there's an extra dimensionality added to it because now you're finding constituents of each jet. So if you look at the type here, what this says is there are 4 events. Each event has a different number of jets. Each jet has different number of constituents, and each constituent is a specific record type. So this is what's happening here. And another thing I want you to notice is that this extra field has been there from the beginning. It was in the input data that went into the cluster sequence class, and it's there in the constituents. So what happened was the cluster sequence class kind of ignored it and just used whatever it wanted to use, what it needed to use, and perform jet clustering on it. So now I can use this extra field or parameter here to calculate a charge of a jet. Really, and due to using awkward array, it's really easy in Python. And as you can see, it has calculated the charge for each jet. And really, the point I wanted to make was that using awkward arrays, data manipulation is very easy. And actually, it was never this easy. So also, when we talk of awkward arrays as the mode of input, we have to ditch pseudo-jet class. So something has to take its place. So that brings us to vector. This is a new Python library which is really made for 2D, 3D, and Lorentz vectors with a physics application in mind. So I'll show you an example of how an input awkward array can be in a different coordinate system and still be a valid input, like here. So I'm sorry, I have to import awkward, import vector, register awkward, and then give this name momentum 4D, and that's it. Now you can perform jet analysis on this easily. It doesn't need to be in a PXP by PZ coordinate system. So in conclusion, I would say that, well, you can pip install FastSet very soon. There's multi-event vectorized clustering now, and also handling the data was never this easy. That was it from my side. Thank you.
Thanks very much, Arjen. Just on time. So we have probably time for 1 or 2 questions, quick questions. Have you got Slido in, or shall I do?
Yeah. Yeah. Was the time scale for first release in PyPy with the basic functionality available? So basically being able to do what PyHEP does at present. Actually, we're very close to the first pre-release right now. And really, it should be a matter of weeks before we're able to release this as a release candidate. And from there on out, as we add functionality to it, maybe new releases will come. But beyond that, I'm not really sure of the release time structure. Using FastSet plugins is just about recompiling FastSet, including them. I'm not sure what you mean. We compile with all the plugins enabled when this Python package is compiled at source, and so they're available throughout the whatever. If you pip install them, all the plugins are available. If I got the question wrong, you can maybe send it on Slack again.
The rest may be a bit better to do offline. I see it's probably that probably requires a bit of discussion because it becomes technical, right? But I think it does make sense to take it offline.
Sure. Yeah.
Okay, and then we stick a bit roughly on time. Thanks very much again. So we now switch on to PyTorch Inferno, which means hell in Portuguese, by the way.
Okay. Are you able to hear and see me?
Yeah, you can start sharing and stuff.
Yeah.
Ready.
This one, I think. Okay. And you're able to see the slides, okay?
Yeah.
Option, there we go. Yeah. Okay. So good afternoon, everybody. I'll be talking here about PyTorch Inferno. this is a Python package that I recently released, designed to be kind of as close as you can get to a drop-in implementation of the Inferno algorithm. Now, to begin by hiding that. Now, what's going on here? It's decided to cut off the bottom of the slides. All right, well, that's annoying. I'll go through it normally. Possibly increase the resolution. Okay, hopefully that's readable. It worked 5 minutes ago, but it doesn't anymore. Okay, so if you imagine just a common, your typical high energy physics search, you're going to do all your event selection, get to the end, train a binary classifier to separate your signal from the background. The loss here is binary cross entropy. You're completely ignoring any systematic uncertainties that you may have on your input features or the normalization of the processes you're considering. You get to the end, you get a very nice separation between signal and background. You bin it and you use it as a summary statistic in order to perform a statistical inference of your final parameter of interest, your signal strength. And it's only now that you begin to consider that you may have systematic uncertainties on your data. Now, if the effect is large, then it's actually going to worsen your sensitivity to the signal, and you're getting worse performance than you might otherwise be able to get. So the Inferno algorithm that was published in 2018 by Pablo de Castro and Tommaso Dorigo. Here you're actually considering the systematic uncertainties during the training of your model. It allows you to directly optimize a deep neural network for statistical inference of the parameter of interest. And the loss here is actually one of the elements of the inverse of the Hessian of the log likelihood with respect to the parameters in your model, your statistical model. Basically, you encourage it to have a steep gradient with respect to your parameter of interest and a shallow gradient with respect to the nuisances. So here's the profile log likelihood of your parameter of interest. If you make this more steep, you get a more you reduce the uncertainty on your inference. And similarly, if you flatten it out with respect to your nuisance parameters, you learn to become more resilient to them. Now, the output of Inferno is already a pre-binned summary statistic. So you have a softmax on the output, and you kind of learn these unordered classes, and they emerge as a function of the training. And this learned binning also then allows Inferno to account for nuisances on the normalization of the processes as well. I'll discuss the algorithm a bit further in a few blog posts that I've linked to here. Now, when you actually come to implement Inferno, you first of all begin by showing the data how it could be modeled, how it could be modified by systematics on the inputs. And then you pass this modified data through the deep neural network. You then, inside the loss function, compute the signal and background shapes, normalize them, and then compute the profile log likelihoods. Differentiate it with respect to the nuisances and the parameter of interest. And then the actual loss that you use is one of the elements of the inverted Hessian. And you backpropagate this as normal through your network and update the parameters. Now, a few of the difficulties here are that the data needs to be modified before it gets passed through the network in order to include the effects of the nuisances. And depending on your framework, you may also then need to reevaluate the model response on data that doesn't include the nuisances to get the Asimov response, the default response with no nuisances. So the aim of PyTorch Inferno is to try and provide a drop-in implementation of the loss, such that you don't have to go in and start modifying the code that you've written for the training loop. And so you can also then interchange it easily with other loss functions to compare the performance. So I chose to implement it as a callback class. If you're perhaps familiar with Keras, you'll know that callbacks are a way to modify the model, the training, the data, aspects of the training without having to modify hard code. Yeah, and they can perform these actions at several sort of interjection points during the optimization cycle. So the PyTorch Inferno package provides a basic training wrapper for PyTorch and quite an extensive callback system, plus all the basic inference system that you need in order to do negative log likelihood minimization in the presence of nuisance parameters. Now, actually including Inferno in your analyses, it's going to depend on your analysis, the nuisances that you have, the processes, the signals. So the best we can do is to provide an abstract implementation for Inferno. The user can then inherit from this and override the required functions specific to their task. Yeah, I've tested the package and it successfully reproduced the paper results on the toy dataset. Now I'll skip through these cells quite quickly. You can go back and read them. Here I'm just showing that yes, the callbacks can interject at the required points during the optimization loop. The data can be modified. So this is one of the main methods you need to override the org data. You take the input data, you can mask it if you want to select signal or background. You can mask to select individual features, and then you show how it would be modified by the systematic, these alphas. Alphas here, they're all at 0, they're nominal values, so you're not strictly modifying the data. All you're doing is showing if the systematic changes, how do the inputs change? And then you compute your loss. So inside the loss computation, you compute the signal and the background shapes. And then you go through and you do your, you construct your log likelihood. Yeah, find the Hessian of it, invert it, and then return the required element of it. So just to see this all in action, we'll look at the paper example. This is just a 3-feature classification problem with nuisances affecting the position and the scale of 2 features and the normalization of the background. So there's a method here to import the data that's included in the package. We define the DNN. This is just a typical deep neural network in PyTorch. We have this softmax on the output and 10 outputs. This is the 10 bins in our final summary statistic. And then we put this into a model wrapper to handle the training, the saving, predicting, and whatnot. Now for Inferno, we set the loss to none because we're going to use this paper Inferno callback. We have some constraints on our nuisances here, so we can say that we know from previous experiments that the normalization is a Gaussian centered, centered to 0 with a width of 100, maybe 100 events. We train it. Now for binary cross entropy, all we need to do is just change the model to be a sigmoid single output. Tell it to use binary cross entropy, and then we cut out Inferno. And then we can train that as well. There's a bit of code here, so I'll just skip over. Basically what we do is we compute the profile log likelihood, and we can see that both of them predict the signal strength of 50. However, because Inferno was trained to become resilient to the nuisance parameters and was made aware of them during the training, its final precision on the parameter of interest is much, much lower than what we get from binary cross entropy. So just to summarize, the PyTorch Inferno package provides a starting point for using Inferno in your own analyses. It's all pip installable, so it's quite quick to try out. As I mentioned earlier, due to the task-specific nature of Inferno, it's kind of difficult to avoid the user not having to inherit and build their own classes. There is an approximation that I haven't discussed here that perhaps could be generalized to work directly on the systematic data sets that you get in a typical HEP analysis. Yeah, and if you don't like PyTorch, the code kind of shows how you can potentially implement it yourself for your own chosen framework. And there's also TensorFlow 1 and TensorFlow 2 implementations of Inferno, so I've linked to that. So thanks very much. I'm afraid I've gone a bit over time. I don't see any questions.
Okay, thanks very much. Sorry. A quick one maybe from my side, interactively. You mentioned these other implementations, but for example, you may have heard earlier today from PyHF that they have different backends. So is this a possible route that instead of having a completely different package, we actually would have different possibilities of using the same algorithm? With the same implementation, but then you could use PyTorch if you feel like it, or
yeah. So potentially. Okay, so there's this a group, Grad HEP. We were meeting a few months ago, and we discussed the possibility, because there's a lot of very similar algorithms. Inferno, Neos. I can't remember the name of it, but or the author actually. But there's a third package, and they all basically do the same thing, but just have different slight changes. So we're thinking that kind of the holy grail would be to have a single package that implements all of these algorithms, and the user is free to say, okay, I want to do histogramming, I want to do KDE for the summary statistic. I want to do this. I want to compute the likelihood, or I want to do I can't remember the name of the technique now, pointwise differentiation. Anyway, basically a single package that does all of these. And I think at that point, once we've all sort of individually worked out how all these subsystems connect together, then maybe we could go with something that is kind of framework agnostic. I think that'd be really cool. Because yeah, I guess at the moment everyone's basically split between TensorFlow, PyTorch, JAX. So it'd be nice to have a single repo that did everything.
Right. All right. Thank you. Yeah, in that respect, again, if you want to have a chat with the people, at least a few of them I know are connected and that'd be good. All right. Thanks again.
Okay. Thanks very much.
So now we move to the last presentation, which is James. Hi, James. Somehow I'm. Can you start sharing? Yeah.
Yes, I can.
So it's got a long title. We're changing gears again, so it's quite a heterogeneous set of lightning talks. That's good. So we have a nice overview of different things. So off you go, please.
Just one moment.
We see the slides anyway. Yeah,
do you see it now? Okay, good. Okay, nice. Thanks to the organizers, and thanks for the interesting talk so far. As Eduardo said, this is slightly changing gears, and it's not a notebook. So I'm going to talk about DEFT, which stands for Differential Effective Field Theory Tool. So what is DEFT? Well, it's a Python tool, obviously, and it aims to do one thing well, which is constrain the parameters of standard model effective field theory using differential cross-section measurements as input. So the DEFT design goals is exactly that: to be simple, to be easy, and to be someday extensible. In a word, it's trying to be DEFT. And it's very much a work in progress. So it's in an alpha state just about. It's living on GitHub right now and can be snooped at the link there. We're definitely not ready to have something really publicly consumable, but we're pretty close to it. And with a little know-how, you can make DEFT work as you might like. And we do have a plan for a stable documented release, I hope within 6 months and maybe within 1 year. Okay, so what does DEFT do? Bird's eye view. So to do a constraint analysis on the SMEFT, you have two basic ingredients. You need the SMEFT itself. You need a theory predictions for an observable that you might hope to measure. So the example here on the top left is the differential cross-section as a function of in-TT bar, so the invariant mass of a top quark pair. And you see a bunch of histograms here which represent the predictions of the SMEFT for various values of the free parameters of the SMEFT, which are usually denoted C, otherwise known as the Wilson coefficients. And they're the free parameters of the theory. We won't get into the physics of it, but they're there and define what the theory says. Of course, we also have measurements of those same observables. Nowadays, we have many, and they're getting more and more precise. I show an example from CMS from a couple of years ago of MTT bar. So they are the two crucial ingredients that come together in order to constrain the SMEFT, and that's where DEFT comes in. First of all, it builds a regression morphing model. That's the name I give it. But really, it's a simple thing. It's just a parametric model of that differential cross-section, so that histogram, or otherwise you could think of it as a vector, as a function of those free parameters. And it builds this parametric model from an array of theory predictions. And then the second crucial ingredient, of course, is the data. And together, DEFT produces a posterior probability density function as a function of those parameters, those coefficients. And if you have n coefficients under consideration, then you have an n-dimensional posterior function. And of course, we like to marginalize that. And DEFT also does that, utilizing some packages that I will talk about presently. Okay, so to brush a lot of interesting physics under the carpet for the purposes of this talk, we can say that cross-sections in general in the SMEFT are nothing more than multivariate polynomials. So they have a constant term, which is the standard model cross-section. And then you have a bunch of linear and quadratic terms, which represent the new physics terms and the contributions that the SMEFT describes. You have a list of contributions that depend linearly on these coefficients, and a set that depend on the products of all pairs of coefficients, including the squares of each coefficient. So you have a bunch of unknowns here because all the linear terms have slopes, which are called beta I here, and you have additional unknowns, which are the coefficients of the quadratic contributions beta ij. So if you could determine the unknowns here, you could work out the SMEFT prediction at any point in the parameter space of the SMEFT. But these unknowns are dependent on the observable you're after and the actual theory calculation you have in hand, for instance, the order of QCD. So what DEFT does is the simplest possible thing you could imagine to determine those unknowns. It simply minimizes the sum of squared differences between the predictions, the theory predictions that you might pull out of these days, most likely MadGraph, and some SMEFT model, and a bunch of predictions of your parametric model. And so if you sum across all bins and all predictions, you get this squared sum, which of course should be minimal if you have the correct values for the unknowns. And that's what DEFT does, typically over a large number of predictions, which are typically much larger than the number of unknowns. And we do this because typically a Monte Carlo prediction will have some uncertainty. And if you over-constrain this system, you become less susceptible to excursions in the model from Monte Carlo statistical uncertainties. Of course, you can test how well your model is doing by just comparing to independent theory predictions at independent points in the parameter space. Okay, so once you have your parametric morphing model of your differential cross-section, DEFT then just employs two fairly well-known and popular Python packages to do the rest. First of all, MC comes in, and what MC does is explores the parameter space intelligently. And at each point, it uses DEFT to produce a differential cross-section prediction, compare it to data, and produce a log likelihood. And that's what you see in the GIF here. You have the exploration of the parameter space, in this case, just 2D for visualization purposes. You have the changing morphing prediction, differential cross-section, matching well and not so well with the fixed data, and then the log likelihood varying accordingly. And then another well-known package, Corner, takes that resultant in-dimensional log likelihood, posterior, and marginalizes it into nice visualizable one-dimensional and two-dimensional PDFs. And from there, it produces Bayesian credible intervals, which are your ultimate statement about the content of your data. On the purely practical side, I hinted that DEFT one day should be extensible and as modular as possible. So an entire analysis is defined in a single readable JSON file, which consists of two main blocks. First of all, you define your data, the bins in which your data lives, the central values, and usually you need a covariance matrix for differential cross-section, as you have interbin correlations due to the unfolding process. That should all be encoded there. Happily, these days, this information is available on HEP data, so can be easily integrated into DEFT. And secondly, you just need the inputs from which the model is built. So that consists of a long list of theory predictions, points in coefficient space to which they correspond. So with those two together, the rest is automated. Here I show an example DEFT analysis that has just arrived on the archive as of yesterday. And it's just the example I've been using to demonstrate the capabilities of DEFT so far. And you see it's the impact of the TWZ process being measured at the high-NUMI LHC in the future, the demo. Okay, so to summarize, DEFT aims to do one thing well, which is measure or derive constraints on symmetric parameters from differential cross-sections. It does this by forming a regression morphing model of the differential cross-section under consideration, and then from there on out utilizes MC to estimate the posterior PDF by exploring parameter space and marginalizing that to produce final credible intervals. It's in an alpha state, but it's progressing quite nicely, most evidenced by the first analysis using DEFT appearing on the archive, and is available on GitHub right now. And we do hope to have something stable, version 1 appearing within 6 months to a year. Okay, thank you.
Thanks so much. So you have a couple questions, 2 or 3 questions, if you want to share them, or I share them. I
see them on Slido.
Sorry, yeah.
I see them, yeah. So
Okay.
I think Grant's question, is it really limited to differential cross-sections, for example, the differential t-bar chart? Yeah, that's a very good question, and something that's very on the tip of my tongue as I'm working on a charge asymmetry analysis with exactly this question. So not in the medium term, it's certainly not limited. Just right now, it's just being designed to work with this multivariate polynomial. So it's just a matter of getting in the weeds and making sure that if we do it for something like a charge asymmetry, and that it would work out of the box. And I just wouldn't be sure of that until I see it with my own eyes. But the method would be very similar. And then an anonymous question says, how does DEFT compare to the traditional EFT method where the beta coefficients are thought to some interpolation of EFT Monte Carlo results? So what I can say is the morphing method that is described in an Atlas note from maybe 2014 gets the beta coefficients from an exact matrix solution. So it solves a matrix equation and gets an exact solution. So in spirit, that's very similar to what I'm doing here. Except if the input predictions carry some Monte Carlo statistical uncertainties, actually some parts of your matrix, your betas, can be quite poorly constrained. So when you actually do your fit to data, those terms become important and are poorly constrained from your initial solution to the matrix equation, you can actually get big excursions in the predictions. And that's what actually prompted this idea of over-constraining the system by using lots and lots of theory predictions and suppressing the effects of Monte Carlo statistical uncertainties. I'm not exactly sure if that was what is being asked by interpolation, but in essence, what we're doing here is fitting the betas first before we fit to the data. Maybe that's clearer.
Yeah, I think so. By all means, again, if there's anything else that comes in, please continue on Slack. So thank you, James, and well, thank you everybody for the very interesting presentation that we had today. Again, it was a really cool second day. So we're finalizing almost on time, so I think still acceptable. It's only 8 minutes past. So we look forward to tomorrow. It's starting at the same time, so 1400 nominally for Geneva time, but whatever morning or evening for some of you. So see you tomorrow, and thank you again. Have a good day. Bye bye.